Melis neden Türkiye'nin en çıtır patates çipsi?
Bilir misin?
Esteemed guests and dear scientists, welcome to the second day of the third International Ship and Marine Technology Conference. Now I would like to present our first keynote speaker of today, Professor Dr. Georgia Trinkas.
Yeah. Yeah. Thanks. So, ladies and gentlemen, good morning. Hope that what I'm going to present can be of interest to you. It refers to application of Russian technology I was acquainted about it almost 30 years ago. And it's very promising for ocean-going ships, as I will try to show today. The paper was written together with my friend and colleague, Professor Naberry, which sorrowfully couldn't attend this conference at the last moment. So, here I don't read, of course, all what I have written here, but what's important is that with reference to current and oncoming rules from IMO, which are terrifying for ship owners, it's absolutely necessary to innovate shipping. It means ships, firstly, in many respects. I'm a ship designer, I'm a hydrodynamicist, and so the paper is referred to which solutions can be given from the hydrodynamic point of view. Yesterday was a very interesting paper about Strathclyde University, let's say, and the figures were very impressive, but more or less they correspond to what Russia, since the end of the past century, succeeded to reach in coastal waters and rivers and lakes inside Russia. So the content is referred to a refitting of a bulk carrier with this technology, the so-called air cavity system technology, which cannot be confused with air bubble or air film technology, which is applied on cruise ship nowadays by DK Group, with results which are not so satisfying from my point of view, but we come later to this. So the presentation is divided into main blocks. Firstly, I want to discuss the reliability of our computer code written by Professor Naber and myself as regards wave-added resistance and effect of waves or weather conditions on the propulsion factors, which is of utmost importance. The second part is dedicated to the air cavity system technology, and the goal is to compare the results which can be attained in terms of speed gains or fuel reduction or power reduction in actual condition. We simulate an actual transfer of the bulk carrier from the Texas to Norway. I anticipate that from a ship owner, I have all the data log of 3 years, which was absolutely necessary to have in order to validate our computer program. Well, the bulk carrier as it is a standard bulk carrier, Panamax size that you can see in the table. Here I anticipate which are the characteristics of the propulsion system. Of course, it's a single screw ship with an engine I cannot specify. It's not MAN, it's not Vassila, okay? And I anticipate the redesign of the propeller, which I've done with the lifting line theory, and this the anticipated result. As you know, bulk carriers sail fundamentally in two loading conditions, the so-called laden condition. It means design condition fundamentally, and ballast condition, which is a big problem since in ballast condition the ship has a high trim, and we will consider it in our simulations. I anticipate also the the propulsion coefficient, which shows that, no, sorry, you see here, the quasi-propulsion coefficient is sufficiently high. It means that the stern shape of this bulk carrier is quite good. When we perform a comparison between, let's say, the baseline ship and refitted ship, it's much easier to start from a bad design. When as a young engineer, I worked in Maya from Geneva. My boss, and I can say my real teacher, Dr. Chupa, was capable once to improve a ship by 32%, okay? I looked at Professor Chupa, Dr. Chupa, and I said, oh, you are a genius. No, it depends where we start, no? He had in his hand from the client a ship which was a disaster. It was quite easy for him to reach such a value. Okay, here I report calculations of added resistance in waves. We implemented, of course, what is generally used by all scientists, all software, even commercial software, the strip theory with the Gerges-Birkemann method, with addition of Maurer's theory for the radiated waves. But these theories altogether are very reliable in head sea, even in following sea, but in quartering seas and in short waves, results are not good. So we introduce also the Faltenstadt method for short waves. And these are the results comparing the ballast and the laden condition in terms of kilonewton. I use only the international system. I have no kilo forces or feet or measures like this. Even though when I'm most involved now in transport of gas and hydrogen too, transport. And I have to use feet, square labels, and so on. Here, more than tables to have immediate feeling of what happens in head sea and in different and I don't see it here, yes. Is head sea? Because we have a lot of people that just someone. Okay. With head sea and following sea, comparing the baseline ship and in two different loading conditions, the ballast and the laden. If you look with some iterations, these curves, you will see that there is not so much difference between ballast and laden condition. I have experience on experiments on seakeeping bases both in Marion and in the Netherlands and Krylov in St. Petersburg, Russia. And if you have to measure seakeeping performance of a ship, starting from motions, in different loading conditions has no sense, because the variation in motion and even in added resistance, acceleration, and so on, are quite small. If you have money and time, okay, data are data. But if you have a restricted budget, don't worry. It's sufficient to measure an intermediate, I'll say an intermediate draft between the two in this case. What is more difficult to achieve is to calculate the propulsion factors. It means fundamentally the wake fraction and the thrust deduction factor, okay, which most towing tanks give you as a constant value, as constant values. Is unbelievable. It's unbelievable. But this guilty is the ITTC, International Towing Tank Conference. If there is someone involved in hydrodynamics, I have not a good opinion of ITTC in the last 30 years. Instead of speaking about experiments, they focus fundamentals on computational fluid dynamics, no? Which a poor tool with respect to experimental basis. And of course, I have my database, which I received with my cooperation with Krylov since '92 up to this terrible war 2.5 years ago. No, and so I have been inside Krylov every second month for 25 years. So I have a lot of data in my database, and it's sufficiently reliable. And you see that the propulsive coefficients change a lot. Mostly the wake fraction, which is the solid lines, with respect to speed and to different sea states. Starting for, okay, it's also camel water, is a brown color, the lower one, and you see that increases the sea state, the wake fraction, fortunately, goes up. It's unbelievable. For resistance, no, we don't like waves, but for the wake fraction, it helps a lot. It can make us very optimistic. On the contrary, the thrust reduction factor decreases too, but in a lower entity. What's important is that the hull, so-called hull efficiency increases. On the right, you will see how the open water efficiency of the propeller changes marginally up to speeds, in this case of 11.5 knots, which corresponds to a Froude number, linear Froude number of 0.1617, which is a value where the wave-making component resistance starts to have some influence, let's say. Here there are the results for the power performance in head C. Of course, the paper is quite long, it's 20 pages. And I couldn't put all the diagrams, all the tables, which I have calculated, drawn, and so on. And so I put the most significant results here. What is interesting is to see that in head C, the difference in power performance between ballast draft on the right side and the laden condition, laden draft on the left side is not so different. It's not so different, okay? This confirms what I was saying you before, if you are in a very initial stage of the ship design, these calculations can be done immediately, can be reduced to some regression formula, which someone suggests me to call AI for. Okay, is it? I worked with statistics and formulation applying design experiment since 25 years, and I published a paper 25 years ago on fishing vessels using what I call like other researchers meta models, and the modern young people call it AI, artificial intelligence. And I received an invitation from an American important magazine to authorize them to publish in their magazine, which has in the title Artificial Intelligence, this paper. This is a crazy word. It's a crazy word, okay? It's marketing. Huh? And so it's not so many, there are not so many differences in this case. I can conclude that what I'm saying about marginal relevance of draft is definitively true, because I have experience in offshore, it's okay. But on RoRo, no. On RoRo ships, no. In RoRo ships, no. On RoRo ships, I even suggest to make calculation and experiment on three drafts, no? Ballast, light load, and full load. I always avoid, by my experience, to come to general conclusions valid for whichever size and kind of ship. So here I calculated is given the results for the baseline ship in still water. Calculations were made for 5 main engines load, and in red I put values achieved for 75% of maximum continuous rating, which is the value required by EDI formula, as explained by Professor Charlie Shah yesterday. It was interesting that our code works quite well, because the baseline ship was designed for a speed of 14.5 knots. So the difference is 0.02 knots, with that is zero, is nothing, okay? And this is comfortable since the first result on the safe side is that you have a very, very accurate calculation of power and performance in calm water. Absolutely. Absolutely. You can tolerate plus minus 1% difference with respect to the sea trials, no more. Okay? Don't use commercial soft codes. If I'm speaking to young naval architects or young students, don't use commercial soft codes. Don't use them. They are not old, they are not updated, they are statistics as regards wave maker resistance of ships which don't exist anymore. For instance, if we speak about the Fisher correlation line of ITTC 78, is based on container ships of the first generation, which had a full number reaching even 0.3 fruit numbers, because they were short at the time, 140 meters, and ran at 23, 24 knots, okay? These ships don't exist anymore, and so the correlation line ITC 78 can be used in the towing tank. They correct it with allowance coefficient, which is different for tankers. They have data, a lot of data, and their figures arrive correct from experiments. But when you are in the preliminary stage of calculations, you have to implement your own software. You have to buy data, data richness. Okay. Well, and here I report in this table for also here for 3 different engines load, the speed achieved in heading and following sea. In the paper there are other heading values, bow quarter C, stern quarter C at least, if I remember correctly. And you see that the achievable speed goes much lower as a function C state in heading C with respect to following C. Here is calculated the fuel consumption. This table here, shows the nominal specific fuel consumption in grams per kilowatt hour at different engines load. These are nominal values given by the provider of the engine to the ship owner. And these are the fuel consumption in tons per hour in 2 different drafts, in heading condition and different sea states. You see that at high speeds, which cannot be reached in any case by the baseline ship, 15, 16 knots. In sea state 7, the fuel consumption is even reaching 4 times the consumption in calm water. And the increase is not linear. It means that you see states 4, 5 as intermediate, which is the mean on an annual basis of wave heights all around the sea states in the world, okay, which corresponds about 2.45 meters in between sea state 4 and sea state 5 is a blue line. Okay, these are the most probable wave heights in the ocean on an annual basis. It corresponds to your table given yesterday, and probably it will appear once again here. Then we simulated on that route from Texas to Norway, where we have data, the data log. What makes this simulation, let's say honestly, a bit academic, is that the company which gave me this data log probably didn't give me the real route they perform in different seasons. Because after I wrote the paper, I had opportunity to discuss with some shipmaster of Grimaldi line who worked before on bulk carriers transport, he said, you are crazy. This route is too long. And in winter time, you cannot go here. Oakland. Yeah. Sorry. Here. Because there are a lot of pieces of icebergs, okay? And so the results are in absolute value very disputable, okay? But since I use the same route for the baseline ship like now, and immediately after for the air cavity system fitted ship, okay, the conclusions can be accepted in relative terms, of course. Okay, and so here you see which were the speeds and fuel expenses in calm water. Then in this table, this one, okay, you can see which is the percentage of time spent in different zones along the route, and the percentage distribution of sea states in each area. And you see that the big majority is here, sea state 4 and sea state 5, in any case, as yesterday in Professor Charlie Shah's paper, okay? You see that calm water with sea state 1 means waves like this, okay, is almost not existent. And I wonder why most of ship owners still rely on sea trials. What for? What for? What for? This is a real ideal utopia situation, we can say. Why? For Russian Navy, the design condition is sea state 6. For US Navy is 4. For Italian Navy, they think that we are, the Mediterranean Sea is at Trieste, in my town, in the northern Adriatic. It's unbelievable. It's unbelievable. Hey, they make things easy, okay. But the ocean is different. And these are the results, okay? In terms of achieved speed, and fuel consumption. These are the results for this route, no? With the limitations that I try to be intellectually honest. The route is too long, and I don't know if it's worse or better if I will follow the indication which I will receive for this shipmaster. He promised to give me the real route in winter time, in summertime, okay, not in annual. Well, then we come to the air cavity system technique. In this table, I don't make many comments now, but these are the marketing proposals in calm water of different technologies, no? Because all these technologies go under the general title air lubrication, okay? But there are at least 3 categories to be distinguished. The air bubbles, the partial cavity, which someone calls also air film cavity, which is an evolution of the air bubble, and what is called air cavity system, or multi-wave cavity system more correctly. And you see that there are two institutions. Stena is a shipping company, but which is historically a very innovative shipping company, sometimes with fantastic results, sometimes with fantastic failures, no? But it happens when you take risk to innovate. And you see that there are more, the one institution or technology promising about 15%. You see, Mitsubishi promised 12%. They applied on 2 ships and they reached 7 and 8, no? In calm water. These values are in calm water. No one tries to, to speak about real situation. I explain here why these technologies are different, and what is interesting is that the other institution was 10 years ago a big European research for air cavity, involved Marvin, HSVA, Mice Group, and other participants. There were 12 cooperants, and they didn't succeed. They didn't succeed, why? Because they have not understood, have not studied sufficiently the bubble dynamics, as the Russians did since the 30s of the past century. There's a problem. You cannot go to experiments without a theory, okay? Trying to copy. You have to combine theory, calculations. I know because I implemented, I participated in recent years in soft implementation with Krylov. I didn't want to make the paper too heavy, so in references you will find citation from Butuzov up to Professor Amaronin, who is in the United States, works in the United States, and but for his safety, he never gave the keys to Americans to arrive to this technology, in any case. And what is different, because someone of you probably is acquainted about supercavitated propellers or ventilated propellers, no? And the technique, the theory here has one difference, that in supercavitated propellers, the cavity must be as long, at least one length, the length of the profile. Here, we will see a photo of the model. The cavity must be reattached to the bottom of the ship. Okay, so the mathematical algorithm changes as based on the potential theory. In any case, it's not much more sophisticated than potential theory for wave making resistance. Okay, here you can see a model of a bull carrier and a sketch, okay, of the cavity. You see the inner fitting, you have to build a false double bottom, okay, to create this niche, and which is the goal? When the system works well, when the profile here of the multi-wave cavity is almost equal to the wave-making profile along the surface. Okay? This is, and this is realized, combine experiments, modifying this wedge here, you see, angular inclination, type of profile put there. So it takes between this interaction, calculation, experiment, calculation, up to the optimal solution, it takes 6 months. 6 months, okay? It's not a routine job, at least in this state. Details of is the meaning of this number 1, 2, 3, 4 you can find in the paper, okay? What is important, I designed the niche. Is important that you cannot, it has no sense to apply this technology when the full number is, linear full number is between 0.22 and 35, 38. It means in the region, in the range of full numbers where wave-making resistance is very relevant. In some condition, it could overcome even the frictional or viscous component. Okay, so the technology can be applied to slow steaming ships, okay, with fluid number below 0.22 and very fast. It was applied by Russian to catamarans, high-speed catamarans, rigs, planing craft, fast navy ships. There are a lot of applications. At least there are about 100 designs in Russia with this technology, no? With real applications. And it's important that you have possibility to have a flat bottom, at least the area of flat bottom, or better, the area which is spent for building the niche, the big cavity, in the bottom, at least 30% of the total wetted surface. Otherwise, it works. Here we are on a small bulk carrier, and I succeeded to have this percentage 32.4, if I remember correctly. We are in the limit. It means the bigger container ship, the bigger tanker, the bigger LNG could get results much higher than in my simulation. I run. We recalculated the added resistance in different states, and you see that the red line is state 4, the brown line is state 7. The difference is dramatic. Is dramatic, no? In head C. In following C, there is some difference, of course, but not so dramatic. Here you have the same figures for the ballast draft, and we calculated then how the brake power was reduced in calm water. you can see that the calm water we are around 19%. On large container ships of 1,000 TEU, I perform some preliminary calculation, you can reach in calm water 24-25% in calm water. Okay. Here you have the curve. Once again, you see between laden draft and ballast draft, there is not such huge difference. No? This is important, I repeat, if you are going to experiment. Don't duplicate, spend money. It's better to spend money to analyze the wake field. It's much more important. Sometimes I cheated the clients as a consultant because the budget was short, and with the towing tank, I agreed to make measurement of wake field and put false points around theoretical calculation, like if they were also experimental calculations, because, you have no measure resistance. Resistance is the much easiest component of the problem. And here we have a table of, you see, reduction in power and demand, different states, different speeds, different heading angles. What is curious at first glance, for instance, look here. You have in strictly Baru quarter and C, the values goes near to the Stern quarter and C. It means that you are in the hands of masters as regards fuel consumption. They have to feel how it's better. Here is the diagrams. In the diagrams, the reduction in speed as a function of significant wave heights. Again, you can see for ballast on the right, a laden condition on the left, okay? For different engines, main engines load. And you see, once again, the difference in the two conditions are quite similar, very similar. And attainable speeds, for instance, in following C. I try to use the same scales for comparison. And these are the final results in calm water, and simplifying in the Atlantic route is a route of simulation. I can say that because of space, I didn't perform economic calculations. I didn't calculate the carbon tax reduction, and so on and so on. Okay, but I performed some preliminary evaluation, and I can say honestly that the cost of the refitting for one ship cannot be recovered even in 15 years by this reduction in fuel consumption. But since bulk carriers like container, like tankers, are built in series, you spend for the first one some $1 million. I finish it. For the second, the third, the fourth, this cost becomes marginal. So this has, for a small size bulk carriers, small size tankers and so on, sense if you are going to introduce that technology on a fleet, okay? For big ships is another, large ships is another story. Thank you. I finished. I don't know how to switch off. She will come. So some questions?
Thank you for sharing lots of information. It will take a while to see how one can apply to real ships and convince the ship owners. But I'm curious about the source of all of these numbers, and are they collected data or simulated data?
No, simulated data. Yeah, I collect data. Of course, I have a lot of data from the towing tank, because as friends they give me, I cooperate to teach them how to write Fortran, for instance, in Marine, no, since the 80s. And then I have a lot of reports of clients for whom I was consulted, or my friend, Professor Nabe, was consulted. So we have a lot, many data. For instance, we use this to build meta models for the propulsion factors, okay? But all the software is written by ourselves, okay? From calm water resistance, calm water propulsion, added resistance, so on, and so on, so on. And we validated because we have contact with some ship owner, and we have some data log. Even I have to criticize them because they don't measure what is necessary to do. They give some data, but not complete as you need, you know, and because culturally, I have my PhD students which are working in cooperation with MSC as regards fuel consumption. They predict, for instance, for past year, a budget of some million dollars for fuel consumption. They failed 23% because they based this this prediction on sea trials when ship is delivered. I'm speaking about cruise ships, large cruise ships, and with sea margin, which applied 15% in Mediterranean. No, you know, it's unbelievable because situation in the world, as you know, climate change doesn't mean only that it's warmer generally, but it means that wind, waves, and so on are different. Current are moving in different directions, and they failed 23%. So now they are starting to realize that they have to make reliable calculation on added resistance. Okay, added resistance, we are good protected. You combine all the old methods of citation, Gerisma, Faltisen, Marot, you come nearby, no? Because it's not so important to reach exactly the peak in the transfer function, because when you average on an annual basis, everything is green, is gray, no? So, coming back to your question, yes, we simulated with our software, which is continuously updated. My power prediction program, I started to write it when Professor Alkan was our PhD student No? Okay. Since then, I'm at a release number 20 for myself. Understand? No? Because it's necessary to that naval architects, professor universities, have to have real contacts with the real world, not to stay closed in the classrooms. Absolutely. Because hydrodynamic theory was written completely at the end of the 19th century. No? There is nothing new to discover. The problem is to apply. We have the mathematical tools, which we didn't have even 30, 40 years ago, only in geometry. Splines didn't exist. I remember when I was in Fincantieri, young designer, I was responsible to develop software, and we bought the foreign system. No? The most difficult thing was to give right information to the cutting machine for flat bottom and flat sides of ship, which were not flat at all, because we use I forget the name of the geometry. We made for a line of 200 meters. Yes, we have at minimum 400 oscillator circles. And so they were not flat. If you by the eye was flat, but they cover with painting and so on. So we have a lot of tools which 130 years ago, 50 years ago, Freud, Rayleigh, and others didn't have. But the theory is there. The problem is to have data and to use data seriously. And I'm not pessimist about AI, because AI is statistics. And data belong to us, understand? No, okay.
May I add, may I ask a little bit, now that we see the variations, then the captain must be well educated on what to do under what weather conditions and so forth. So how do you predict that?
When I have a good contact with three masters in Italy. Very experienced. Now they are entering their 60s, and they say, for instance, one of them 2 years ago was in charge to drive a new PCTC pure car truck carrier of Grimaldi Group. The ship, one of the 7 ships up to now, was built in China, designed by Knudsen. He wrote me in some metaphoric way. I understood that he was not satisfied. When I met himself, he told that this ship was a disaster. He was on a sister ship on the next travel, and once I received an email where he said, I succeeded to go back to a ship who was 12 years old, the PCTC of the first generation, because it was quite better in 3 state conditions. When there was a state, the ship has an involuntary speed reduction, 3-4 knots. In sea state 5, 3-4 knots in sea state 5. And vibrations and what have you, weeping phenomena and so on and so on. So he said, but what are you teaching in the universities? Because they are right. He is right. He's right. He's right. They teach to write for guys, clever guys, because there are a lot of clever guys. I can say that my generation was worse than many students I had as a professor. But we were much more curious. We were much more curious. We were skeptic with respect to professors. We were skeptic, put questions. No, I feel myself with students like God. No one, any objection, It's unbelievable, unbelievable. They are like mentality like soldiers, but they are talented. When I work with them in diplomacies or PhD, I saw they are many very talented, but they must be guided properly. And I told, you want to calculate with CFD? Which CFD? Have you developed your own code? As much as I know, I was working with viscous problem up to 98, no? And I was using the K epsilon turbulence model, no? And even now they are using K epsilon, and K epsilon model was developed in turbo machine field. Reynolds number 10,000, no? Our Reynolds is much higher. We have to flow to fluids. And it's unbelievable. I said them, before you have to develop your own code, but first you must be able to calculate analytically. You must have your own benchmark also. No? There's a problem. I don't know if you agree, according to your experience. Yeah? Yeah.
Could you wait for a second? We will
Yeah.
give you a second.
What?
Excuse me. Yeah, I
Introduce. Okay.
I'm free?
Could you wait for a second? Present placket.
Professor Trinkas, thank you again for accepting our invitation to be our keynote speaker. He already presented all the efforts. I know him since 1990s. Thank you very much. There is another improvement, I think, with the air bubble technology, 2 digits, as Professor Atlar yesterday speaking about 2 digits of improvement. You had also with the, I hope it will be applied by the ship owners. Excuse me, an announcement. The halls B and C are ready for their paper presentation. You are invited to those halls B and C. Türkçe olarak da söyleyelim lütfen. BVC'de BVC'deki oturumlar başlıyor. Buyurun lütfen. Now the plaque ceremony. I think you have question.
Yes, the time passed so much, but anyway, it's okay for me to give a question now. Yes, I think in order to evaluate the fuel expense or speed loss in severe sea states over 6 or 7 at A, in case of large, even though the ship is very large, I think there is a propeller emergence. So it makes the speed loss more, and I think in order to evaluate the fuel expense a little accurately, I think the number of propeller emergence or like force order motion relative to wave should be considered. How do you think about that?
Professor Dr. İsmail Hakkı Hayvacıoğlu and Professor Dr. Ahmet Dursun Alkan for President Plaquette for Professor Dr. Trinkas. Here is the phones.
Yes, the keynote speech continues for a long time, so we start the session 6 a little later, but it's okay that we have originally 6 papers, but now 1 paper has been canceled, so it's okay? It's okay. Yeah, but I think Dr. Mehmet will reduce the time of the presentation. Anyway, I am this session chair. My name is Hyungkyu Yoon in Changwon National University in Korea. Yes, thank you. Let's start. Please.
Yes, good day to everyone. I will be quick as much as I can, and today I will present you our study about comparison of two initial stability condition and how this initial stability condition influences the ship motion response during flooding. I will start a little introduction to the subject and we'll go on with the study, and I will be quick. And as we all know that ships can occasionally encounter various accidents, and there are many reasons to these accidents, and the accidents that can damage to the hull may compromise the watertight integrity of the ship. And when the hull sustains damage, water can infiltrate to internal compartments, and this additional mass of the water can destabilize the vessel and endanger the lives on board and the equipment and cargo on the ships. And assessing the flooding dynamics in damaged vessel is a very challenging process, and because it's influenced by many factors, and these factors also influence each other. For example, there is a free flow on the damaged location, and there may be internal compartments within the ships. So even when compartment is damaged and water begins to fill the compartment, the water can progress through the internal compartment, and also the presence of watertight compartments helps preventing the flooding. And we also do not forget that excessive water intake can lead to sinking due to insufficient buoyancy. And yes, if we look at these factors a little more in details, there are ship characteristics, damage location, water ingress rate, air entrapment, non-watertight compartments, and air environmental conditions. And as we said before, like for example, the environment conditions like waves would affect the ship motion, and ship motion affects the flooded water motion, and the sloshing occurs in the ships also affect the ship motion, and ship may affect the water around it, and it goes on like that. So every factor is, there is an interplay between them and the ship motion, and in order to make a accurate assessment, we need to know the interplay between them. And if we want to divide the ship flooding into phases, in general, we divide it into 3 phases. That first phase is the transient phase. In this phase, the rapid accumulation of flood water in the compartment may quickly heal the ship to a large angle. And if there is internal openings to the damaged compartments, the progressive phase begins. In the progressive phase, flood water gradually spreads to the other compartments through these openings. And if the ship doesn't sink or capsize during this phase, it eventually reaches a steady phase in calm water, or a quasi-steady phase in waves. And as we said, during the transient phase or progressive phase, the ship may capsize or sink due to buoyancy limit. And this happens very fast, even less than a minute. It can capsize the ship or sink the ship. And due to the complex dynamics of the ship flooding, understanding the behavior of damaged ships remain primary focus of these studies. Yes, because the ships moves in 6 degrees of freedom, it's very challenging to account for all these factors and the interactions between them. And to study the damage stability, we have 3 methods. We can study through experimental, numerical, and theoretical methods. And each of these methods has its own advantages and disadvantages. And when I make this study, I check the global merchant fleet first, and I decided to study through the ro-ro ships, because the ro-ro ships are designed to transport wheeled vehicles, such as automobiles, motorbikes, and trucks. And these ships also have other types to meet the needs of the industry, such as pure car carriers, pure car and truck carriers. And the model I work is RoPax ships, because the RoPax ships carries both passenger and wheeled cargo, and they face some stability issues. And in our study, the initial stability condition, we just compared the metacentric height for our case. There are many factors, and they can be studied through many cases. And in the study, we used a model ship designed by Meyer Türk Shipyard in compliance with SOLAS standards, safety standards. And because this is the continuous study of a project, I modeled this ship in 1:112 scale. And in those projects, we weren't able to make the experiment for the flooding process, because it happens too fast, and the ship model was very small to do that experiment. The overall length was 1.435 meters. And because I couldn't able to make experiments with the model, I used the CFD methods. And the damage compartment consists of 3 separate compartments. One compartment had watertight separated from other 2 compartments, and one of the compartments were connected through internal opening. and the compartments does not fully filled with the water, so it has a sloshing motion. It had a sloshing motion. Yes, the two GM values we studied is, one of them is recommended, higher of the recommended standards, and one of them was lower of the recommended standards. And the numerical model is start with the numerical ship model. Because I use overset meshing model, I had to prepare a component zone and background zone. What really happens is the component zone is moving within the background zone to able to simulate the motion of the ship. And the background zone was in that time was the size of the background zone was equal to the wave basin. And this is the mesh structure for both background zone and the component zone. And even with computational fluid dynamics, these fluiding cases are very computer dependent, very takes too much to calculate. And this is the boundary conditions for the numerical domain. There is a pressure inlet and pressure outlet, boundary conditions. And to prevent the wall effect, the other sides are symmetry. And the boundaries of the component zone is overset interface, and the ship is wall boundary condition. And yes, with the CFD, we were able to capture the fluiding process perfectly, and velocity, pressure, and other variables. And the good thing about CFD, in the experiment, we should open the damage to fill the ship with water, but in the experiments it's pretty hard to do, because even with the tiny touch, it affects the ship motion. But in CFD, we were able to separate the water from ship with an invisible layer and start the fluiding through there. If we see, the ship instantly start to fill with water, and this is the comparison of two initial condition effect to the mass of the fluiding water. In the initial stability condition in our case did not affect the mass of the fluiding water that much. It is pretty close. This is mostly affected by the damage location and size, so water ingress rate. And this is the angular motion responses we get from our simulations. And because the metacentric heights are different, the lower metacentric height had more maximum roll angle during the fluiding, and this also causes the ship a little more yaw response. And the pitch motion is, in our case, was similar, and the linear motions also are very similar to the each other with different initial stability condition. Yes, in this study we try to understand the effect of initial metacentric height difference on the fluiding and motion response of a damaged ROPAX ship model with using ground space CFD analysis. And as we see, the variation in GM1 and GM2 minimal effective water ingress rate, as both configuration exhibit similar fluiding water masses over time, and stabilizing around 3.6 kilogram in approximately 10 seconds. In the end, both GM1 and GM2 eventually converge to minimal roll angles, but higher metacentric height demonstrates lower maximum roll angles caused by the sloshing water. And pitch and heave water in this case are largely unaffected by the initial stability conditions. And yaw motion is a little more pronounced and less damp with the lower metacentric height. And we can say that these kind of studies may help in the emergency responses and safety of the ships. And if you have any questions, I can answer them.
Okay, thank you.
Thank you.
Yeah, now this paper is open to the floor. Is there any question or comment? Yes, please.
Thank you for the presentation, but I'm following your, I think it was slide number 5, the flooding that you showed after the first compartment.
Yes.
The other compartment failed as well. Do I understand correctly?
Yes.
Now, following this CFD post-processing, you show.
Oh, okay.
Yeah, this one. Yeah, that's one. So let's say the starboard compartment is intact at the beginning, but then it collapses. Is it the idea? Or?
Yes, the damage extends to both compartments, this compartment and this compartment.
And then the bulkhead, the longitudinal bulkhead fails.
Yes, and then the water start infiltrating the compartments, this
Yes.
and this is the internal. These compartments fill through the internal openings.
So there's a structural failure there.
Yes.
Oh, okay. I was wondering if that's the case.
Yes.
I mean, that's understandable because from Titanic, we understand that the main problem was the material. It contained lots of sulfur. It's not the design, but the high sulfur content of the steel actually made the whole process fail.
Yes.
So, thank you for the.
Thank you.
Thank you. Is there any short questions? Yes.
Maybe I failed to pay attention enough, but there is some comparison between experimental and CFD results.
Yes, in that time we weren't able to carry out the experiments because our model was small.
Yeah, because the model is quite small.
Yes, so we use numerical methods for that.
Because I worked in this field for 30 years ago, and I realized that models must be as large as possible.
Yes, around up
for
over
instance,
5 meters.
The crazy Russian in an old debate in IMO succeeded to demonstrate that Andrea Doria was lost because there was enough buoyancy. The master was educated to transfer through cross-flooding water from myself. He transferred too much, but was not educated. And when there was the court of law in Italy, he was considered the unique responsible for the disaster. Like Master Schettino for Concordia ship,
Yes.
I can speak about it privately because a bad Italian story, okay? And the model which scientists in Russia built was 14 meters.
Yes.
14 meters, understand? With their unbelievable tanks, so on. And they discovered a lot of things. For instance, what the group of my friend Professor Vassalos demonstrated here, that sea states, no, can be even on the convenient side in flooding situations, no. So I expect that you have possibility to make experiments and to confirm the CFD results.
Yes,
Thank you.
maybe in future studies. Thank you, Professor.
No question? Yes. Thank you for presentation, Dr. Jenner. Please give big hand to Dr. Jenner.
Thank you.
Okay.
Yes.
Yeah. Next paper is comparison of ocean maneuverability prediction methods, top fitting versus transfer function. Yes, please.
Thank you. Good day. As the presenter of the study, I would like to begin briefly introducing myself. I've been working a research assistant at Department of Ship Hydrodynamics in National Defense University. I will discuss the preliminary findings from a part of my PhD research related to the topic at the hand. Furthermore, this study conducted in collaboration with the Bulgarian Academy of Sciences was supported by Scientific and Technological Research Council of Turkey. I will cover the topic listed in the slide throughout the presentation, which consists of 35 slides. In our study, we estimated the unknown hydrodynamic derivatives of the 1 degree of freedom first-order linear non-mathematical model using the TRR optimization method based on system identification. We analyzed and validated the model's predictive performance by systematically comparing with experimental data. In order to mathematically express the behavior of the ship and find the trajectory of the ship, or to keep the ship controlled as a autopilot on the desired course, we need to know the heading angle of the ship with high accuracy. For this ship we use in this study, as detailed in our prior study, instability was observed. Holding the rudder at the midship of the midship position resulted in both sides positive and negative yaw rates. This instability shows the necessity of an autopilot system to maintain the vessel on its intended course efficiently. Let me briefly explain the concept of ship stability using this figure. If a ship is subject to an interaction caused by external force such as wave, current, and other ships, and after a while it gets rid of these external forces, the course keeping ability vary according to whether the ship is stable or not. If the ship is stable, the ship retains its original heading and moves parallel to its initial course. If the ship is unstable, as we see in the figure at the bottom, the course will lose its straight line path. Without rudder application, course would be deviated and the ship will follow a circular or zigzag path. To prevent this, in our future studies, we plan to use PNID autopilot system proposed by Fossen in maritime system simulator to maintain the desired course. This system involves unknown parameters that vary with rudder angle. For standard maneuvers, these parameters must be calculated. In our example, we focus 35-degree turning circle maneuver, which will enable the ship model to navigate this maneuver autonomously in the future study. In this study, we analyzed experimental maneuvering data, estimated hydrodynamic coefficients using system identification method, and such as curve fitting and transfer function, and validated the mathematical model by testing its ability to predict parameters like heating angle and yaw rate. Finally, we evaluated the model's performance by comparing simulation results with experimental results. There are several methods available for estimating maneuvering performance. Common techniques include empirical methods, computational fluid dynamics, experimental approach, and system identification method. For this study, we use system identification method to predict ship maneuvers. In this section, I will talk about experimental data source which we use in this study. A 4-meter length model ship is the car carrier called SPSRA1. The primary geometric characteristics of this ship are presented in the table. Also, this SPSRA1 model is equipped with one right-handed Wageningen B-series propeller with 4 blades and one rudder with NACA 12 profile, as shown in table. In the table, you will find the test data from the maneuvering basin at Bulgarian Ship Hydrodynamic Center, where a turning circle test was conducted, as I said before, 35-degree to starboard side rudder angle to gather steady-state yaw rate data, which is presented in the table. The data in the study is specific to a car carrier ship type, and we assume calm and deep water conditions. Now let's focus on Nomoto mathematical model, particularly the characteristic of turning circle maneuvering test. For a basic scenario of turning circle test where the rudder is suddenly moved to an angle delta A and kept fixed, as we've seen in the screen, the yaw rate are in equation 1.1 is described by a first-order linear differential equation. The analytical solution to this equation indicates that the yaw rate increases exponentially with its growth rate influenced by t and ultimately converging to a steady value of k plus k delta A, as we see here. Tabii, pardon. Now, in this subsection, I will explain the application of system identification used in our study. As shown in the figure, we use this approach to fit the coefficients and parameters of Nomoto mathematical model. Initially, we utilize or use MATLAB system identification toolbox to estimate these parameters, and then we applied a second model, curve fitting method. Offline system identification uses statistical methods to develop mathematical models of dynamic systems based on input and output data collected during experiments. In this process, the error denoted as epsilon represents the difference between observed and predicted output. This error minimized of the squared errors. Additionally, n refers to the size of training data, which is in this study 477 observation taking at 0.1 second intervals. The parameter vector theta here, theta, which is varies depending on the mathematical model, is estimated through this process. Let me explain the relations in maneuvering dynamics. When analyzing maneuvering test data, we generally find no linear relation between yaw velocity and yaw rate, yaw acceleration, and delta due to the ship's nonlinear behavior. As a result, the parameters K and T known as maneuvering indices, depends on delta. K reflects the ship's turning ability, while T represents the dynamical stability, indicating how well the ship follows rudder commands. These indices are influenced not only by the ship's dimensions and shape, but also operational factors, vessel velocity, loading condition, trim, draft, and water depth. The differential equation in equation 1.1 describes yaw motion as a second-order response to rudder commands. However, assuming a fore and aft symmetry, this model is often simplified to first-order differential response, as shown in 1.5, making it widely applicable in controller design. In the first-order model, Nomoto model shown in equation 1.1, there are two parameters, as I said before. These are K and T. Since the derivative of PC in this equation PC, corresponded to R, a single input, ship dynamics are modeled as a second-order differential equations. Our objective is to transform this second-order differential equation into a matrix equation as displayed on this screen. To simplify the parameter estimation process, use this state and output equation. K and T indices can be determined using several methods. One of the methods involves using transfer functions. The Nomoto index equation in 1.5 can be derived through transfer function with the help of Laplace transform, as we see in the screen. The K and T indices can be determined for both methods. The system identification process follows a very similar approach, which we will explain more clearly in the subsection. For now, let's take a quick look at the overall process on the screen. First, the required information is defined. Next, the system identification method should be applied. And finally, the prediction performance of the model is evaluated. And let me first explain the transfer function method. Firstly, using the TRR optimization option in system identification toolbox of MATLAB, this method was applied to iterative minimization. One key advantage of TRR method is its ability to handle parameter constraints, upper and lower bounds, effectively compared to other line search methods such as gradient, adaptive Gauss-Newton, or Levenberg-Marquardt method. The second method we use is a curve fitting method applied through MATLAB's curve fitter application with a TRR optimization option. This approach not only optimizes the parameters, but also allows us to examine the residuals as we see in the screen, giving insight to unpredicted positions of data for yaw rates. We conducted a study to evaluate the results we obtained in terms of maneuvering performance. On the screen, you can see the Nomoto indices derived from these applications, both applications, presented individually for comparison. We obtained similar coefficients, as you see. We aim to simulate the turning circle test using two models we created based on coefficients we obtained. To achieve this, we developed and implemented the scheme you can see on the screen. In this section, I will give our findings related to this study using MATLAB Simulink environment. Two different methods for obtaining coefficient of mathematical models were compared, and models gave approximately similar result with the experimental test IV1. Both models IV41 and 51 predict yaw angles well, with IV51 slightly better than IV41. The differences are small, suggesting both models are effective in predicting in yaw angles during turning circle. Similarly, on the screen, we can observe the simulation result for the yaw rate or yaw velocity. The differences are small, suggesting both models are effective in predicting yaw rate or yaw velocity. The IV41 model had the lowest computational time, and the IV51 model predicts the ship's heading angle better than IV41 model. The IV51 is better for precise prediction of maneuver. The IV41 is better for less computationally intensive solutions. Computational effort for curve fitting is low due to simple models. This method is rapid and effective for application requiring steady-state predictions. When we evaluate the methods overall, as you can see on the screen, both have their own disadvantages and advantages. After observing that there was not much difference between two models, we decided to extend our study. We decided to extend our study with the transfer function method, as it proved to be more reliable than curve fitting. I will now share the first findings of our study. On the screen, you can see the model obtained using transfer function number IV51, along with the comparison of Nomoto coefficients for different rudder angles. In the application section, we discussed that both K and T Nomoto coefficients are dependent on rudder angle delta. This table and following graph supports our findings, showing that as the rudder angle increase, K and T coefficients decrease. A smaller T improves the ship responsive to rudder inputs, but a decrease in K negatively impacts the turning ability. That is, turning circle diameter will be higher or increases. In this section, I will present the result of this study. The result validates that TRR method using data from free running test is a reliable and accurate approach to illustrate ship yaw motion and predict hydrodynamic coefficients of Nomoto mathematical model. I would like to point out some marks that can be added to this work in the future. Maneuvering operations carried out much more in the port area compared to open sea. The water is usually shallow in these areas. For this reason, knowing the behavior of the ship in advance when passing from deep water to shallow water is important in order to prevent possible accidents. In the future study, autopilot navigation is aimed by designing a controller. If these coefficients can be calculated by itself with online system identification, the algorithm will constantly renew and improve its mathematical model automatically. We have started working on conducting our future studies with a real ship model, motor vessel, BBNA. In this context, we received support from Yıldız Technical University Scientific Research Projects Coordination Unit for our multidisciplinary scientific research project. We equipped the container ship with an engine for propulsion, IMU for positioning and measurements, GPS, LiDAR, a rudder, and servo motor to control the propeller. In the next 1 year, we will conduct studies for autopilot navigation in phase 1 at the hydraulic laboratory in Yıldız Technical University, Davutpaşa location. Then we aim to conduct autonomous navigation studies in phase 2. We have started, as I said, we have started work for studies for phase 1. In order to validate our system with existing full-scale sea trail data, standard maneuvering tests are planned to be carried out with 1/58 scale model of this ship, container ship, in the following days. This presentation summarizes our research on predicting the ship maneuvering performance of a scaled car carrier using system identification methods, focusing on TRR optimization options. It demonstrates how this approach can contribute to development of safer and more precise navigation strategies in maritime industry. Thank you for your interest, and now I'm open to questions.
Thank you. Okay. Question or comments? Yes.
Presentation, one quick extension of your work. As you may know, one of the very dangerous areas for maneuvering is Turkish Straits. And Turkish Straits are known for their currents. And I'm wondering how you can possibly extend your work to include currents and such other parameters that do not exist in your presentation.
Thank you for your question. We didn't include, or our study don't cover currents where these are exclude forces. We will add these forces after this research. These are our future research. Thank you. Istanbul Bosphorus has lots of current, as you say. So we know we need to include these currents to our mathematical model. But for now, I don't know how to explain how we can add this term, a current term, to Nomoto model for now. Thank you for your question.
Any other questions or comments? Yeah.
Very simple question. Have you, for this ship, have you considered some criteria to check with respect to no motor indexes?
Which criteria?
I wonder which criteria to apply when you use no motor coefficients. There are some criteria.
We assumed that fore and aft there is a fore and aft very similar, and left and right and starboard. Sorry. We assume that this is a calm water and a deep water. And actually, I didn't understand the criteria question.
Yes.
For Nomoto model.
Yes. Yes. Yes, because it's clear that you have a parallel course, no? Like in the first slide. It shows the first slide. What's the first slide?
Bir dakika.
Oh,
Burada bir şey yok.
slowly. No? No, okay. Okay. How to judge if the course is stable or unstable? Exposed is easily.
Normally, we have to do spiral test for understanding the ship is stable or not. We did this research, our prior research, with MMG model, not Nomoto model, and we see yaw rate for right when we turn the rudder to right side, we obtained yaw rate, we obtained a yaw rate 0.2, not 0. If we find 0 yaw rate, we can say the ship is stable. But we found. Thank you. Now I understand your question. Thank you so much.
I share a comment with you. Thank you for the presentation. In the last 5-6 years, we had in Turkey we had several maneuvering research studies. I should say the names. Dr. Özden and Dr. Kınacı, they had free running maneuvering model, experimental and numerical they studied. Also, Dr. Atasayan works on that. We hope to improve these studies. Yes, as Professor Çalışal stated, there are many risky regions for maneuvering as Marmara Straits. The gate rudder and some kind of innovative rudders will help to have better maneuvering. I think the time is limited. I give just few comments. Thank you.
Thank you. I have a very short question. Yeah. Actually, I'm a little strange that you used KT model, Nomoto's KT
Yes.
model. I think that is a linear model.
Yes.
But you used the tight turning circle test result.
Sorry?
I mean, the 35 turning circle test is very tight maneuver. That means I think the nonlinear phenomenon affects the final result of turning circle test. So in my opinion, it is better to apply the
Non-linear terms.
MMG or Evkovich model instead of KT model. How do you think about that? Yeah.
Thank you for your question. Actually, we want to combine with Nomoto model. Actually, we have a desired heading angle, and we after this process, we have a commanded rudder angle, and this commanded rudder angle will supply, will go to directly MMG model. So this process just give us a rudder angle. So we will obtain non-linear ship maneuvering with MMG model. this section just only give us commanded rudder angle. We know here is linear, and we know there are second order non-linear Nomoto models, and we are working on it. And in the future, maybe we can renew this section with not first order linear model, with second order non-linear model. We are working on it. Thank you for your question.
Yeah, thank you. Yes, thank you for presentation, and please give big hands to Dr. Atasayan. Right? So, next presentation is experimental investigation of the effect of Bilge Keir geometry on roll damping.
Hello, everyone. It's an honor to be here with all of you today. Sorry. I'm Ayşegül Saraç and a bachelor's degree student in the Department of Naval Architecture and Marine Engineering at Karadeniz Technical University. Today, I will be presenting the experimental investigation of the effect of Bilge-Keil geometry on roll damping. This study is carried out by me, Hasan İslam Çopuroğlu, Naofumi Yoshida, and Emre Peşman. To talk about the contents of the presentation, we will examine it under 4 main headings: introduction, experimental method, results, conclusion, and discussion. As is well known, ships have 6 degrees of freedom: yaw, heave, sway, pitch, roll, and surge. According to research, roll, heave, and pitch are lead to more significant negative effects compared to other movements. In this study, the damping of roll motion, which is one of the 6 degrees of freedom, for a parallel body model with different Bilge-Keils, was investigated using experimental methods and image processing techniques. The particle image velocimetry technique is used to visualize flow structures and enable to comparative analysis between rounded and sharp Bilge-Keils. The experiments are conducted in the Ship Hydrodynamics Laboratory of the Faculty of Marine Sciences in Sürmene. As a result of this study, the behavior of the parallel body model with varying Bilge-Keil configurations in the fluid and the vortex effects of the fluid are analyzed. So, to talk about the experimental methods, to begin with the parallel body model. The parallel body model was created using the CAD modeler program, was designed based on the values provided in that table. The model includes a parallel body and 2 detachable Bilge-Keils, one with a rounded design and other with a sharp design. As you can see, it's the sharp design, and that's the rounded design, which equals to quarter sphere. This design was printed using PLA material on a 3D printer located at the faculty. Due to slight oversizing caused by temperature changes, the sliding sections of the printed Bilge-Keils were thinned using a sanding machine. 800 grit sandpaper was applied to all surfaces to minimize surface roughness. As the model came out in 6 separate pieces, it underwent assembly with epoxy adhesive and then received a coat of spray paint. Following the painting process, as shown in the figure, the joints were sealed with waterproof tape for additional protection. And for the roll mechanism was modeled using Rhinoceros 3D software. The system consists of 4 bearings, 2 bushings, a rod, 2 lateral support plates, 2 hanger plates, and a wooden base to secure the mechanism to the tank. To ensure axial balance, the rod was aligned with the kg of the parallel body. The tank characteristics are displayed in the figure. Once cleaned, the tank was filled with water by taking into account the length of roll mechanism and the draft of the parallel body. A solution containing 10 grams of microsphere particles mixed into 0.8 liters of water and was added to tank. But what is the purpose of using these specific microspheres? The answer is these microspheres reflect laser beams effectively, and so they ease to observe the fluid motion and its direction. And that's the PIV system that we used. As seen on the system, the model is placed inside the tank on a position that can get face to laser's beam. The laser machine settings were adjusted to 8 amperes and a wavelength of 532. A camera mounted on a tripod was aligned directly across from the bilge keel to capture the frames on the right position and angle. And the experimental steps. The model was adjusted to float at a 0.065 meters draft without trim or heel. After stabilizing the model with a weight, the weight was removed to perform the test. The model was released from a roll angle of 30 degrees. In the frame captures, the motion of the model between 0 degrees and minus 30 degrees was separated into 20 frames. Each frame was processed to improve the image quality. Following this, the parallel hull was masked, and the area for velocity vector calculations was defined. And inaccurate vectors were removed to ensure clear and accurate results. And the same procedure was repeated for both bilge keels. And here you can see the masked area, and this is the defined area. To see the velocity magnitude results and angles, we can check the image, but I would like to take your attention about the scale difference that I will explain about it in a while. That the scales are different because it is hard to observe for the rounded bilge keel the velocity magnitude because the colors are not seen when the scales are the same. So to talk about the angles, for frame 1, it's 0 degrees. Frame 5, 8 degrees. Frame 10, 16 degrees. Frame 15, 24 degrees. And frame 20, 30 degrees. As I mentioned, to better observe flow structure and behavior, the velocity magnitude scale was adjusted differently for the rounded and sharp bilge keels. The main reason for that is when we use the same scales, it is so hard to see the fluid structure for rounded bilge keel. But in the vorticity analysis, where the scale was kept the same for each, the difference between the two bilge keels seems much more observable and sensible to compare, as the scales are exactly the same, and you can see that the difference of the fluid structure for the both bilge keel. And it is well seen that sharp bilge keel shows larger vortex regions than the rounded bilge keels on the same angles. And as I keep going, that you will see it better. And the angles are the same again. For frame 1, it's 0 degrees. For frame 5, it's 8 degrees. For frame 10, it's 16 degrees, 24 degrees, and 30 degrees. As you can see, at the end of the motion, nearly at the end of the motion, that the sharp bilge keel has bigger vortex areas than the rounded one. Examining, analyzing, and observing the dynamics created by the fluid around the hull during roll motion, as well as studying the resulting flow patterns, are essential for minimizing the harmful effects of this motion, such as capsizing, sinking, and so on. So for the final words, in this study, the roll and damping characteristics of a model with different bilge keel configurations are investigated experimentally. Additionally, particle image velocimetry is used to visualize the resulting flow structures from a different perspective. As observed in the study, the model with a sharp bilge keel shows larger velocity fields and vortex regions around the bilge compared to the rounded bilge keel. Therefore, it can be inferred that the sharp bilge keel has a higher roll damping coefficient than the rounded bilge keel. And thank you for your attention. If you have any questions, I would like to answer.
Question or comments? Yes, please.
Thank you for the presentation. I have one question about the PIV results.
Okay.
And the vortex at the beginning. So how many frames have you recorded? Do you know how many frames?
20 frames.
20 frames.
But to see the difference better here, I added only the first, the 5th, the 10th, the 15th, and the 20th.
And you calculated it with what kind of program? In MATLAB, maybe?
Yeah, it's related to MATLAB, PIV Lab
PIV
program.
Lab.
Yeah.
Okay, thank you so much.
Thank you for the question.
Yes, any other questions or comments? If no, thank you. And please give a big hand. The next paper is experimental and numerical investigation of effects of force speed on bilge keel roll damping of roller ship. I think this is the second part of the former presentation, right? Yes, please.
Thank you for Chairman. I'm Naofumi Yoshida from Osaka Metropolitan University. So let's start my presentation. My presentation content is 4 points. First is the introduction. To reduce the roll motion of the ships, it is important to increase the roll damping. And roll damping caused by bilge keels, like this, accounts for a large proportion proportion to the total road damping. Ikeda's method is well known as a method to estimate total road damping, including AVHQ component. In recent years, the particulars of the ships has been changed. Since 1980s, when Ikeda's method was developed. Therefore, it is difficult to estimate the VHQ load damping accurately in some cases, regardless of the force speed. Improving Ikeda's method is needed for safety assessment in the ship design. In the case without force speed, for example, Katayama investigated the effect of the recent hull form on the VHQ load damping and proposed some improvements of the Ikeda's method. In the case with force speed, though Ikeda et al. Proposed the estimation formula with the effect of force speed on frigate, but it is unclear whether the formulas are available for other types of ships. So I investigated the effect of force speed on VHQ load damping of a railroad ship, and through the experiment and numerical simulation. And I say idea how to improve, how to take the effect of Ikeda's method is also discussed. The second is road damping. Road damping is can be expressed by using B1 and B2. B1 is linear road damping, and B2 is non-linear road damping coefficient. And also, it is expressed by using B44. It is equivalent linear road damping coefficient. And the equivalent road damping coefficient in Ikeda's method is written as you can see. This is calculated by summing up 5 components. And the VHQ load damping coefficient is obtained from 2 components. And to improve VHQ load damping, to improve Ikeda's method with force speed condition, Ikeda, 1994, proposed the VHQ lift component using Jones theory, and this is VHQ lift component. And in this year, Ikeda and Katayama proposed a VHQ lift component improved by considering the second term that is inversely proportional to the force speed, like this. So is about subject ship. This is the real photo and the 3D model of the roller ship. And the right table shows principal particulars of the subject ship. So I explain about the experimental condition first. Ship speed is 9 k's, and the low amplitude is 3 cases, and the low period is 1 case. And without force speed, the ship set as a normal to towing direction, and with force speed, of course, the direction of the ship is same as towing direction. And this is the numerical conditions. Left is shows the calculation conditions, and the right table is condition of the first order test. In numerical simulation, roll amplitude is only one pattern, and the ship speed and the roll period is the same to experiment. And this is the boundary condition of the calculation region and the particle density of the safety. As you can see here, the distance between particles at the dentist is around BHK, and this is 0.003 voltmeter. And this is the analysis of the measured data. Two equivalent linear load damping coefficient. First is this is the say it's roll motion equation of the first order test. Let's say it's because first order test, so roll is obtained from roll amplitude and roll frequency, and to this equation we can get this equation, and from measure roll motion using full seed free seed expansion, and we can get say it's amplitude of roll moment and phase difference. So using this equation, equivalent roll damping, equivalent linear roll damping coefficient P44 can be obtained. And I use this equation for non-dimensionalized P44, and to get BGK component it's calculated by subtracting the results for the model, without the BGK, Beer-Hall condition, and with BGK condition, by subtracting with BGK, subtracting the result of without BGK from the result of model with BGK, we can get the BGK component. This is these figures show comparison of the time series of roll moment of Beer-Hall condition, and blue line is the result of CFD, and the orange line is the experimental results. This is for with BGK condition. In some cases, I can see little difference between experiment and numerical results compared to the Beer-Hall condition. However, quantitative agreement is the same. So the experimental results are considerable. From this result, B44 and non-dimensional B44 and BHK component are obtained. This is a relation between B44 and the full number. This figure shows BHK load damping coefficient and full number. From right figure, as you can see, BHK load damping coefficient is become smaller around the full number equal about 0.1, and then it increase. So I explain about two idea to improve Ikeda's method. Left figure is a BHK load damping coefficient, and it is the result. It includes formula proposed by Ikeda, though 1994, and the right figure is in this year proposed by Ikeda and Katayama. And comparing two figures, raw full number, it is better than Ikeda and Katayama proposed formula is more good agreement. But from this year, full number is around 0.1 is not enough. This is maybe because high pressure distribution changes with force speed as shown by Ikeda's doctoral thesis. And the reason of this is the change of direction of vorticity set by BHQs. So, conclusion. First is the Newton-dimensional BHQ load damping coefficient is obtained by subtracting the measured moment of the bare half from that on the half with BHQ. And its decreases at full number is around 0.1 and then increases. New BHQ rich component proposed by Ikeda and Katayama is used to express the effect of force speed, and the estimated results are compared with the measured results. The estimated results agree with the measured results better than the estimated results by previously proposed method by Ikeda et al. And the decrease in the damping at full number is around 0.1 is not expressed by proposed formula. The reason may be that the decrease in high pressure caused by the shed vortex in transport direction caused by BHQ. And to clarify the phenomena, full number is around 0.1. More detailed investigation by EFD and CFD are required. Thank you.
Yeah. Yes, please.
Thank you for your presentation. My comment is, I remember that there was a series of publications showing the effect of the pitch angle or trim angle on the performance of the bilge shields. And the conclusion, I think, was that bilge keel starts working like a long wing, very short in length, but the long wing, and it contributes substantially. And I'm wondering if you think that it's worth adding the trim angle in your calculations.
In my experiment, trim angle is 0. But actually, with 4-speed condition, ship has some trim angle. So thank you for comment, and I explain. Sorry, I will do experiment with some trim angle. Thank you.
Yes, please.
Thank you for your presentation. You used a CFD program to validate your experimental results.
Yeah.
And which CFD program you had used? Flow 3D?
It's, sorry, I didn't explain. It is Xflow.
Xflow.
Xflow.
Oh, sorry, yeah. So it uses Lattice Boltzmann equations.
Yes, that is
So
Boltzmann method.
do you have any comment on this, please? Because it's quite different than the rest of the CFD programs. So do you think any effects on the results, and do you have any comments on this?
Okay. As you can see, in Beerhow condition, it's the result is almost same result. But with BHQ condition, I see the calculation results has some difference between the result. Between from the experiment result. Because let's say it's to get the phenomenon caused by BGQ, it's difficult to calculate. Let's say it's with some with this particular density. So, to get more accurate results, particle density in the number of particle densities is a lot, and I calculated like more dense condition, and maybe it took 2 weeks to finish calculation. So I think the problem of it's lattice Boltzmann method. Thank you.
Yes. I have a short question. It's similar to Professor Kaliser's questions. Yes, when you perform the experiment, you make a free for only roll motions, not heave and pitch. Right?
Yes, 1 degree of freedom. It is only roll
if
motion.
so, I think the C44 value could be changed depending on large roll amplitude. So I'm not sure it is such effect is negligible or not, but if you have a new experiment, I think that is better to check such a phenomenon. Yeah.
Thank you.
Yeah, thank you. Thank you for presentation. Next presentation is the impact of general arrangement changes on probabilistic damage stability analysis of a diesel electronic yacht. Yes,
you.
please.
Welcome everyone. I am Arda Can Akbaş from Yıldız Technical University. I am working with Dr. Yasemin Arıkan Özden. I'm also working as a naval architect at Turquoise Yachts. The case is a side study of my thesis, which is to investigate the changes of Index A in terms of changing the propulsion system. This is an encountered problem also in our shipyard. The question is born from the question that we are encountered in our industry, actually. The changing the propulsion systems directly changing the general arrangement of the yacht. So the general arrangement is one of the most crucial elements of the yacht design in terms of the functionality and the comfort standards. In comfort-based general arrangement, the distances, the distances of the transversal bulkheads are increasing, and the large lounges are creating huge, dangerous problems for the damage stability. Comfort-driven requests leads to designation of high-volume compartments that I mentioned. One of the key factors influencing how these layouts are designed, compliance with the stability regulations and calculations. For example, in this case, not in this case, but the other cases, for shell doors have insufficient seal heights according to the flag authorities, must take a risk assessment to provide the regulations. Along with providing large compartments, adjustments are also made to the arrangement of engine rooms to meet the layout requirements. Due to the positioning of machinery, it may sometimes necessary to fit smaller engine rooms within the general layout, which may require optimization through different arrangements that affect the guests and technical areas of the yacht. In conventional yachts, due to the location of the engine room, the shaft arrangement, and angled engines may not allow the placement of the intermediate decks at the engine rooms. On the other hand, the engine room of a diesel-electric yacht can provide a flexibility in general arrangement. The change in general arrangement directly affects the ship's damage stability characteristics. The case of the study is to understand how Index A changes with different propulsion systems. To understanding this and the procedure of the probabilistic damage stability calculations, a validation study conducted. In this study, a Wärtsilä design offshore supply vessel is used with code name 4879101. Code name is given by the thesis author, which is used for the validation study. Calculations are made for 4 different vessels with 2 different general arrangements in the study. And each general arrangement is used for 4 different vessels to understand the longitudinal positions of the U-tanks, how they are affecting the Index A in terms of PDS calculation. The main particles are shown in the table provided by Tersan Shipyard. The buoyant hull of the vessel is also provided by the Tersan Shipyard. In this study, the Jupvik, the author of the thesis, used a NAPA software for the probabilistic damage stability calculations. But in this validation study, we used Bentley's Maxsurf for it. The general arrangement and the bulkhead arrangement of the vessel is shown in the screen, provided by the open source items of the study. For study, I already mentioned, the vessel No1 is used for the validation. First vessel is compared by means of the hydrostatic characteristics, and a good agreement is obtained by means of all characteristics, and the comparison of displacement and longitudinal center of buoyancy is shown on the screen with table 1. Off perpendicular, design waterline, 4 perpendicular were positioned at the designation points following the locations specified in the study. Tanks and compartments modeled according to bulkhead arrangement also, since no specific loading conditions are given and provided, virtual loading conditions corresponding to the displacement values matching with the draft values required for the calculations were created. As you can see from the table 2, with 3 different draft values. We fix the draft values, trim values, and the heel values, and get the other results, the other particulars. Zone lengths, deck heights, longitudinal bulkhead positions are modeled according to open source documents. PI values depend only on the geometrical arrangement of the bulkhead and zone boundaries. Therefore, as shown in the model table, there are no differences between the thesis model and the validation model. It continues with the with vertical extents of the damage, but in this table, I only show the longitudinal extents of the damage. The table 4 represents calculation results for 3 different loading conditions with different adjusted zones. In this case, the thesis uses only 5 zone adjustment because increasing adjusted zones are becoming 0 at the PI value. Calculations have resulted with 0.39% of differences between thesis model and the Jupwix models attained index A value. The results show the accuracy of the calculation procedure followed. After the validation, we modeled a yacht to understand our questions, and this model is modified from our model desk, from the model desk. A straight bow type motor yacht is chosen to understand the case in this case. The idea behind of it is a bulbous type of yacht is converted to a straight bow yacht. The requirement of the PDS calculation may change according to the load line length. Tank volumes, compartment volumes are chosen according to the similar yachts in our desk. Modeling of the buoyant hull is made with the Rhinos Grasshopper because of the parametric coding is needed with that for further questions, for further studies. And the model exported for using for the PDS calculations at Maxsurf. Two different arrangements are designed to understand probabilistic damage stability calculation to change between a conventional type of diesel yacht and diesel electric podded system. In the first one, 2 Caterpillar main engine were chosen to satisfy the cruise speeds. In this case, it's 12 knots. Speed, machine, and fuel tank volumes are obtained by iterations from the similar yachts that are produced in our facility. The other parameters are neglected because of the PDS calculations. And the other case, two Waptec diesel engines are chosen because it does not need a urea-based after-treatment system, and it's IMO 3 emission compliant machine. And two Cummins alternators are supplied for the electrical power for the pod system. And two Volvo generators are placed. Also for the first arrangement, it is also placed at that system. Since there is no need for shaft, an angled engine is also replaced with Waptec engine. With this modification, an intermediate deck could arrange in the engine room. The rudder system and stern thruster is replaced with the pod system. After modification, two more compartments are added for batteries, and two void spaces are created for the safety measures at the battery rooms. On the other hand, the stern thruster is removed from the system. The stern thruster compartment is removed from the aft compartment. So I'm continuing with the calculating the probabilistic damage stability. For index R, it's a specific calculations for all, for also cargo ships and also the passenger ships. In this case, we are calculating it for the passenger ships. The index R varies according to the subdivision length and the symbol N, which depends on the person number on board and provided lifeboat number. PI factor only dependent on the geometry, as I mentioned earlier, of the watertight arrangement. PI is the probability of a specific damage on the ship. Total PI for whole ship length has to be equal to 1 in this case. Not in this case, in all probability cases. After damage cases, an extent of them defined, the calculations of the PE is finished. Calculation of the CE factor is dependent on the survivability of the vessel after specific damage case. With calculations of sub-indices, the attained index A is found. The sub-index A's are calculated with weighted values to find attained index A. In this case, AS represents for the deepest draft, AP represents for the partial draft, and AL represents the lightest draft. The weight values comes from the service times of those drafts. As we can see from the two arrangements, arrangement B has an intermediate deck at the engine room, which is zone 5 and zone 6 for arrangement B. Zone 6 is the arrangement A, the engine room. And we add a transversal bulkhead at the engine room that I mentioned before. It is for the safety measures for the battery room. And we remove the stern thruster compartment at zone 3. As we can see at the arrangement A, it is zone 2 and 3. For conclusion and the results, as you can see, zone 3, 4, 5, and 6 has different values at the table above table. Zone 3, 4, 5, and 6 has different PI values because of the changed general arrangement and bulkhead system. And it has been observed that placing an intermediate deck to a divide to high volume engine room creates almost no differences in the index A. One of them is for arrangement A is 0.79 and the other one is 0.789. But if we calculate it with the deterministic stability, we can see a huge differences for the engine rooms. In further work of the research, more specific changes will be scaled up to a major level to understand the effects of the index A. For an example, this is one of the idea to put in a symmetrical tanks subdivided with longitudinal bulkheads and connected with cross-flooding valves, and we will obtain the perfect positions of the longitudinal bulkheads with calculating different positions and getting the result from the index A. Thank you for listening. Are there any questions?
Yeah, are there any comments or questions? Nothing? Yes, we don't have much time, so it's better to...
Thank you.
Yeah, thank you. The final presentation is development of ship maneuvering motion simulation at low speed using machine learning. Yes, please.
Okay. Thank you for the chairman. I am Ms. Kinugasa and a PhD student in the Osaka Metropolitan University. Today, I'd like to talk about development of ship maneuvering motion simulation at low speed using machine learning. This is the outline of my presentation. Firstly, I would like to start about introduction. In order to reduce accidents caused by human error and operator fatigue, social implementation or maritime autonomous surface ship mass is expected, and most control methods on mass system are model-based control methods that use mathematical maneuvering models. Obtaining the parameter for practical mathematical model costs a lot of time and money. So therefore, it is doubtful whether any maneuvering motions can be accurately simulated by the mathematical model. Therefore, a low-cost estimation method of a wide range of maneuvering motion is needed. In the related work, Wakita et al. And Furukawa et al. Proposed recurrent neural network-based methods to estimate maneuvering motion from free learning model tests of a test bed of a tanker ship. And it was confirmed that maneuvering motion, which maximum yaw rate is about 3 degrees per second, can be simulated approximately. And on the other hand, we propose deep neural network-based methods to estimate maneuvering motion from simulated maneuvering data of a small boat. And it was confirmed that estimation accuracy was varied greatly depending on evaluation methods. However, their issues remain subject to debate. First, estimation accuracy for vessels with large yaw rate is not clear. And effects of evaluation methods on estimation accuracy for measured data and investigated. Third, the velocity is close to zero and the relative estimation error becomes larger. Therefore, the purpose of this study is to do these three things. First, a maneuvering motion of a fishing vessel, which maximum yaw rate is about 20 dig per sec, was estimated by deep neural network, and the relation between inputs and outputs of motion equation by using measured depth. Second, the data set is split into multiple subsets according to velocity, and each subset is run on each model. Finally, calculation was conducted using 3 evaluation metrics. Second, I'd like to talk about free-running model tests. The subject ship is a 1/11 scale model of the Fisher's research vessel named Takamaru. In order to measure the maneuvering motion, a free-running model test was carried out at the Marine Dynamics Basin of Japan Fisher's Research Institute and Education Agency. In the free-running model test, the model ship was operated randomly at low speed. Here, the randomly maneuver. Here you can see the example of trajectory. Here, the randomly maneuvering were carried out by amateur boat operators, and therefore intended data didn't contain in this study. And in the test, forward velocity U, lateral velocity V, yaw rate R, propeller revolution NP, rudder angle delta, and burst thruster impeller revolution NB are measured at 10 Hz. Now, this test was carried out 10 cases to obtain the data whose total measured time is 30 minutes. Here you can see the distribution of forward velocity and yaw rate. The maximum forward speed is 1.2 meters per second, and the maximum yaw rate is about 20 dig per second. Then I'd like to talk about outline of machine learning. 9 of the 10 measured data were used for training, and 1 used for the validations. The measured data are smoothed by 21-point moving average method and normalized from -1 to 1. Here you can see inputs and outputs of neural network model. Inputs are forward velocity, lateral velocity, yaw rate, propeller revolution. Inputs are forward velocity, lateral velocity, yaw rate, propeller revolution, rudder angle, and burst thruster impeller revolution at current time step. And outputs are the forward velocity, lateral velocity, and yaw rate at next time step. And other neural network model, deep neural network and ResNet were used. Here, the equation of deep neural network and equation of ResNet model. F is a nonlinear transformation function, and xt plus dt is output, and xt is inputs. A deep neural network runs sum of acceleration at next time step and velocity at current time step, and estimates and velocity at next time step. On the other hand, ResNet is a model that has bypass connection and merges the inputs into outputs. In other words, ResNet only runs accelerations and estimates velocities at next time step. In the case of maneuvering motion at low speed, if the acceleration is small, it is better to estimate acceleration at next time step by ResNet model than sum of acceleration and velocity by deep neural network. And in order to improve estimation accuracy in near zero values, the data set is split into multiple subsets according to dimensionless velocities. In these studies, the split into 9 subsets, and each subset is run by each models. So in these studies, data set split into 9 models, and making a 9 estimation model is considered. The effects of evaluation metrics on estimation accuracy were investigated. This table shows a structure of neural network model. Calculation is conducted using TensorFlow libraries. Then I'd like to talk about learning results. Here you can see mean absolute error of estimation error. Note that estimation error is difference between dimensionless measured velocities and estimated velocities. In this table, DNN MAE means that training is conducted using deep neural network model, and mean absolute error as evaluation metrics. First, mean absolute error of estimation error by ResNet model were less than a deep neural network model. So ResNet model were better than deep neural network model. It can be seen that ResNet model estimates velocity by learning the acceleration. So it works effectively in the low-speed maneuvering where the ship acceleration is small. And compared to evaluation metrics, ResNet MAE model were better than ResNet MSE model. This figure shows comparison between measured and estimated dimensionless yaw rate. Determination coefficient is the same, and slope of regression line is the same. However, the bias of regression line of MAE is better than MSE model. This is because MSE of evaluation metrics is sensitive to outliers than MAE. And ResNet MSE model is overfitted by outliers. Finally, compared to ResNet model and LSTM model, LSTM is a kind of recurrent neural network which is proposed in previous studies. Compared to ResNet MAE model and LSTM MAE model, the ResNet MAE model were better than LSTM model. And this slide discusses the estimation accuracy with split model of ResNet MAE. A vertical line indicates the estimation range of data set. Here, this from 0 to 1 indicates the learning result on a single model, and G others are learning results of split model. Mean absolute error of split model is less than single model except for below 0.02 of dimensionless yaw rate. So, estimation accuracy was improved by splitting model. It can be seen that the difference between the maximum and minimum outputs becomes relatively small, and the estimation error near the minimum value can no longer be neglectable. Below 0.02, estimation accuracy was decreased due to the accuracy guarantee limits of the sensor. Finally, I'd like to talk about estimation results of maneuvering motion. According to the following flowchart of simulations, maneuvering motion was estimated. First, rudder angle, a propeller revolution, and bow thruster impeller revolution were given at each step. Next, estimation model was switched according to each velocities, and estimated velocities at the next time was estimated. The estimated velocities were used to update the next inputs, and estimation is iterated. This figure shows comparison of estimated velocities. Black lines are measured results, and the others are estimated velocities. Estimated velocities by resonant mind model as blue line was good agreement with the measured velocities, black line. And estimation trajectory by resonant mind model, blue line, was approximately agreement with measured velocity as black line. However, it was gradually deviated from the measured trajectory. This is because accumulation of estimation error of heading angles. This slide shows comparison of with and without switching models. Black line is measured velocities, blue line resonant MAE model, and orange line is resonant MAE switching models. Estimation accuracy with switching model was rather worse than that without switching model. The cause is thought to be a programming error, and as for the future, the reason will be investigated. In the conclusions, in this study, input and output relation of maneuvering motion of the Fisher's research vessel was learned by deep neural network using free learning model test data, and following conclusions were obtained. First, neural network learns the inputs and outputs relation of maneuvering motion at low speed with a maximum yaw rate over about 20 dig per sec by a total of about 30 minutes of data. Second, it was better to use the mean absolute error as the evaluation metrics for the measured data, including statistical noise, and other inaccuracies. Splitting the dataset into multiple subsets according to velocities and learning them on each model improved estimation accuracy. Finally, estimated velocities using resonant MA model were good agreement with the measured velocities. Thank you.
Question or comments? No, nothing? Because of lunch? Yes. Yes, if there is no questions, okay, it's better to finish. Yeah, thank you. Yeah, this session is finished. Yes, enjoy lunch. Thank you.
I will leave you with the video. Unfortunately, he couldn't come here for the presentation, so he has kindly shared a video for us. So I will now start the video.
Herkese Kore'den selamlar. İsmail Bayezid. Aranızda olamadığım için öncelikle özür dilerim. Gerçekten çok üzgünüm. En yakın zamanda umarım İstanbul'da ya da Türkiye, Trabzon'da Türkiye'nin farklı bir yerinde görüşmek dileğiyle. So, hello everyone. This is Ismail Bayezid from Autonomous Ship Research Center operated under Samsung Heavy Industries located at Daejeon, Republic of Korea. I would like to first start to thank to conference committee, especially to Congress Chair, Professor Ercan Köse, Congress Secretary, Professor Hasan İslam Çopuroğlu, and Congress Scientific Committee member, Professor Ahmet Dursun Alkan. I'm fully thankful to all committee members and Turkish Chamber of Marine Architects and Marine Engineers as inviting me as a keynote speaker to this important event and as the organizer of Third International Congress on Ship and Marine Technology. I am working as a principal researcher on developing autonomous control algorithms for Samsung Heavy Industries, small and big ships. Today, I am planning to present you full autonomous ship technology for the perfect safety. Shortly to introduce myself, my background from electronics and control systems engineering of Istanbul Technical University as a double major, and then I did my master degree on ITU Electrical Engineering Department, especially focused on control systems for advanced vehicles. Afterwards, I moved to Canada for 4 years in order to complete my PhD study in the Mechanical and Mechatronics Engineering Department of University of Waterloo. Currently, I'm working in Korea, one of the research centers of Samsung, named as Autonomous Ship Research Center, as a principal researcher. My current responsibilities: model-based design and testing of Samsung autonomous ship system, autonomous berthing and unberthing of Samsung Sea Shuttle, which is named as Shift Auto, and real-time validation of Samsung autonomous ship system collision scenarios. I have long years of industrial and university experience, especially on advanced vehicle technologies in marine and aeronautics grades. Today's agenda is to give the state of the art of autonomous vessel development in Samsung, which is Samsung Autonomous Navigation Research, especially including core technologies, autonomous navigation technology elaborated under Shift Auto, Samsung Heavy Industries featured transportation, and simulation capabilities will be introduced. Shift Auto Remote Control Center also will be elaborated and introduced, and I will close with the final comments. So, firstly, I'd like to start with the purpose and current state of art for autonomous vessel development, especially in Samsung Heavy Industries. Our main business, as you may know, is LNG vessels, big ships, over 200 meters. LNG vessels have 26 to 28 crew members, with trial and application of some autonomy solutions. Expect to allow vessels to operate with up to minimum crew members. Our ultimate goal is to increase safety and reduce operational expenses, OPEX, by replacing crew's work. However, there is a big hurdle, which is difficulty of retrofit and trial due to time and cost. You know, the shipping companies, as soon as they get the ships, they are very busy due to transportation of some goods or some other energy products, And a little bit conservative as a result of this, it is a kind of hurdle or bottleneck for us to implement our technologies, especially on the big ship side. And it is not possible to see trial and carry it out wherever we want to go. We are focusing on commercializing autonomous navigation products especially for large vessels, but we felt some technologies in planning or development stage are needed to be conducted within our own test beds, not large ships first. So this graphics is giving our current station and ultimate goal lines, and what is the bottleneck in between. This is the outline of Samsung core technologies. We would like to classify our core technologies interface with 3 clusters: situation awareness, decision making, and system control. And we also classify as sub-layers platform capability and simulation capacity. Decision-making layer takes care of autonomous navigation, auto-mooring, unmooring, auto-berthing, unberthing, and collision avoidance, especially based on COLREX regulations. System control layer mainly operates for actuation control and manages heading, keeping, waypoint navigation, straight line following, and so on. Station awareness is fully developed by Samsung engineers and manages sensor fusion and 360 degrees surround view. Platform capability makes autonomous technology more compatible and functionable. This is including IoT system, over-the-air OTA system, VHF, and so on. Simulation capability can make it more reliable, which is including real-time simulation capacity and hardware-in-the-loop validation ability, as you have seen as the sub-layers in the very below side of this presentation. Welcome to the Shift Auto. Our future transportation system and approach. This is mainly named as a Samsung Autonomous Ship Test Laboratory. This is the final target is to see all these well-tested technologies, as I mentioned in the previous slides, well integrated on Samsung big ships. This is the Shift Auto, as you see in the upper figure, pictures. We named this as the world's first floating laboratory. So we tested many autonomous algorithms, hardwares, and technologies over this system before employing these technologies on our big vessels. The opening ceremony take place especially end of October, approximately 1 month ago, within Goja shipyard of Samsung Heavy Industries. So we also like to give the expected development time frame of the technology. We already tested and validated our technologies on small ferries and some test big ships, like approximately 100 meters, a little bit lower than 100 meters, and one test ship is 150 meters, for instance. So our SAS, Samsung Autonomous Ship System, is well tested, and also we are certifying this technology with some classification companies. Now we reflect all of our knowledge, like know-how and expertise on Shift Auto Catamaran. Our system already manufactured, and now we are testing and coring ocean using many mission scenarios and COLREX scenarios, definitely. The target is to achieve and finalize human in the system, which is the integration mission, and expect more human intervention during ship operations, which is planned to be approached in the mid of 2026. And human on the system, which is AI supported, fully autonomous vessel, which is planned to be approached within the 2027 and aligned with IMO regulations, other classification companies, flag state regulations, and usable by many countries, and he's been serving for the prosperity of humanity, especially in the business side. Please enjoy the video on capabilities of our Shift Auto Autonomous Ship Test Laboratory. As you see, we are also posting 3D printed. So the progress history, as you have seen in these figures, how we developed this, and then he meets with the Korean waters. The list of capabilities of our Shift Auto, as you see in the previous videos, our Shift Auto autonomous ship test laboratory is considered full autonomous. Ship compliant with core regs includes autonomous navigation and berthing, unberthing, and auto mooring capacity. You can see the exterior and interior design of Shift Auto shortly after this slide. This is the picture on your left side. This is the docking facility, can be shown. As you see, it has been started, the idea planning in 2022, and then afterwards in 2023, basic design and performance estimation finished, and in 2024, production and building docking facility completed, and it was delivered to the Goja shipyard of Samsung Heavy Industries in October 17th. Demonstration starts as of then in Goja shipyards. I will show some videos, especially afterwards. Okay. This is the exterior design. Hull part is normal catamaran, but upper part is very special. Our vice president and the first time when they watched the design, they were really said to us to like it was first, like the initial design was like a bus type vessel, first generation. However, we like to go with this current second generation, is more hydrodynamic-wise efficient, and the vessel quality and performance also well-proofed and tested, and this is one of the best capacity catamaran with the 12 meters length and some other important properties, not only with the hull design and like hydrodynamics performance wise, also the integration of the sensors wise and fully internal and external usability wise is the best test laboratory that we are planning to validate within the years all of our autonomous technologies. So it is a high-tech exterior, and it is being kind of a vision for future maritime mobility. The interior design is focused on comfort for passengers, featuring large windows on both sides to enhance openness and integrate seamlessly with the perfect cockpit design. The cockpit design provides unmanned concept, just monitoring interface, and simplified to deliver a futuristic image, as you see. There are many screens within this one, and then you can, as the passenger within in the Shift Auto vessel, transportation vessel, you can follow up all navigation and autonomous mission during your operation. These are the specifications. As you see, the gross tonnage and total weight, breadth, speed, and all other parameters have been provided. The maximum speed is 9 knots, for instance. There are 2 outboard azimuth type engines. There is one bow thruster tunnel type on this one, and the other parameters as you have seen in this one. So this is the autonomous mission. The autonomous mission is mostly like check, define autonomous mission, autonomous mooring, like it is kind of unmooring, mooring release, and then you unberth from the docking facility, and then you start the DP functionality, standstill, and then afterwards you define your navigation missions and autonomous navigation starts and collision avoidance if there is any static and dynamic surrounding objects. It is recognizing emergency situations. As soon as red flag opened, then there will be human pilot can take the control very easily. Otherwise, either autonomous pilot or request control of the land can be taken care of the control of the ship. Remote operation, as I said, however, we mostly prefer the autonomous operation. We can define mid waypoints and target waypoints and then follow up easily. And then as soon as we come close to the special docking facility designed especially for shift auto, we keep the standstill position, arrange the heading, and then we do start the auto berthing and the auto mooring fully autonomously start and complete our navigation mission easily. Digital cockpit is, from now on, I would like to introduce several autonomous technologies as the core technologies. Crews and officers in the ship is sailing while controlling all navigation system and interpreting complex data in real time. So this cockpit should be more simplified and user-friendly interface. Digital cockpit of Shift Auto displays only necessary information to operate the vessel on single displays such as heading, speed, and navigation data, which informs the crew on board about the ship's current operation mode, either autonomous or...
My research areas focus on enhancing the mechanical properties of shipbuilding materials. Also, I am working on current fusion welding methods and also alternative solid-state welding methods about the shipbuilding materials. With your permission, I wanna like to move on to my work. Today I will talk about the heat inputs and carbon dioxide emissions, and also mechanical properties of submerged arc welding, gas metal arc welding, and also friction stir welding shipbuilding materials. Here you can see the contents of my work. Firstly, I will give general information and then give information about the experimental procedure of my work. Then the results, obtain and discussion of the results, and finally I will give the general results and the presentation. Ships are built by joining together plates cut and shaped in various size by welding. Although shielded metal arc welding and tungsten inert gas metal arc welding also used in shipyards for special materials or special applications. Generally, it's known that gas metal arc welding and submerged arc welding is used on panel lines of shipbuilding materials. Also, it's known that the solid-state welding methods such as diffusion welding, friction stir welding, and also ultrasonic welding, where the temperatures during the welding remain well below the melting temperature, have been used recently as an alternative to fusion welding methods. Also, it's clearly seen that the friction stir welding can be used in shipyards as an alternative to existing fusion welding methods in terms of its application to plate type materials. I want to talk about friction stir welding. In friction stir welding, the stirrer pin immersed in the place, advance at the specified rotation speed and advance speeds, and thus ensuring the joining of the plates. In this method, softened material is transported from the front of the tool to trailing edge, and during the friction stir welding, temperatures is below the melting point. In this study, we measured the temperatures, and temperatures measured at approximately half of the melting point of these materials. This process mixes a material without change the phase and creates a new microstructure and finer grain microstructure. Also, a quick and uniformly distributed grains occurred after friction stir welding. In this method, tool geometry, tool feed parameters, and tool pressure force are the most important parameters. Mechanical properties occurred after friction stir welding change accordingly changed in these parameters. Tool feed parameters, I wanna say again, tool feed parameters, tool pressure force, and tool geometry is the most important parameters in friction stir welding. In this study, we used 10 millimeter thick steel plates used in ship building. Low, medium strength ship materials we used in this study, and friction stir welding, also submerged arc welding and gas metal arc welding is used to joint these plates. As you show in the table 1, submerged arc welding and gas metal arc welding parameters can be shown in table 1. Also in friction stir welding, 800 RPM tool traverse speed used. Also 35 millimeters per minute were used as tool rotation speeds in friction stir welding. Also tungsten carbide materials used in the stirrer pin in the friction stir welding. In calculation, emission calculations were made for carbon dioxide emissions for 1,000 millimeter weld sim. When I calculating emissions originating from the electrode and energy were calculated for submerged arc welding, and emission originating from the protective gas atmosphere were added to gas metal arc welding. Also in friction stir welding, only emissions originating from the energy were calculated because as we know, there is no filler metal, there is no protection atmosphere, so only emission originating from energy were calculated for friction stir welding. After these calculations, we done some mechanical tests. In this test, hardness, tensile, and three-point bending tests for formability were performed to determine mechanical properties, and also comparatively these mechanical properties were evaluated in the study. And also the heat inputs achieved after welding is shown in table 2. As expected from the calculated thermal inputs, the highest heat input was reached in submerged arc welding. This is actually quite an expected result because, as all us know, the main reason for this situation is the high current values used in submerged arc welding. and the use of thicker electrodes in submerged arc welding. Also, this situation done. Submerged as a result of these high heat inputs, we know that submerged arc welding is generally preferred for welding relatively thicker plates in shipbuilding process. Also, table 3 shows the emissions values calculated for the each submerged arc welding, gas metal arc welding, and also friction stir welding. As expected, the lowest emissions values were reached in friction stir welding. The main reason for this, for the increased in emissions values for gas metal arc welding is the gases used as a protective atmosphere. After the interaction of high temperature and protective gas, relatively high emissions values occurred during the gas metal arc welding. Also, the hardness values based on welded samples are shown in the figure. As can be seen, the main materials hardness values increase at all of weld centers. And the hardness values increased. The hardness values increased 210 after submerged arc welding. Also 197 after gas metal arc welding, and 245 hardness weakers after friction stir welding. Table 4 shows the strength and the total elongation values of the base and welded samples. As can be seen, the highest strength values in the weld region were reached after friction stir welding. It's thought that increase in strength values after friction stir welding is related to grain refinement that occurs after friction stir welding. We know that in friction stir welding, a dynamic recrystallization occurs in the welded region. As a result of this dynamic recrystallization, a finer grain microstructure occurred in the welded area. As a result of finer grain structure, the high strength values increased extensively, as we shown in the table 4. And finally, table 5 shows the bending force and displacement values during bending test. As can be seen, after friction stir welding, where the highest strength values obtained, the force during bending increased as expected. Also, as a result of decreasing elongation values, as a result of microstructural changes, the lowest displacements valued were found after friction stir welding. To summarize the results of the study we obtained in the study, the lowest heat input occurred during friction stir welding, and also highest heat input occurred during the submerged arc welding. And also, the lowest emission values during welding were calculated for friction stir welding, and the highest emission values were calculated for gas metal arc welding, almost 8 times that of the friction stir welding, higher emissions calculated during the gas metal arc welding process. After all welding methods, the hardness values of the weld area increased compared to the base material. Also, the highest hardness values in the weld area occurred after friction stir welding with 245 hardness weakers. After all welding methods, there was an increase in the strength. There was an increase in strength values compared to the base material, and the highest strength values in weld area were reached after the friction stir welding with 568 megapascal. And finally, while the bending force values increased after welding process, the displacement values formed during bending decreased also, while the highest bending force value was reached after friction stir welding with 513 Newton, and lowest displacement values was also reached after friction stir welding. Thank you for your participation and listening. Thank you very much.
Okay, thank you for your presentation. Mr. Sekban. And any question to the presenter?
Hi, thank you very much for a very nice presentation. I'm wondering if you were also interested in the Charpy V-nut tests or, at cold temperatures and so forth. The ships normally operate in cold waters as well. And
Thank you, Professor. I worked impact test in my PhD thesis for shipbuilding materials with friction stir welding. In impact test, the impact values increased after friction stir welding comparatively also based and also gas metal arc welded materials. The highest values reached with friction stir welding with the impact test. Thank you.
Okay, one more question. Could you pass the microphone, please? Yeah.
I have a question. First, the stir welding has a limitation of the thickness.
Yeah.
And how much, plates covered by this thickness in terms of naval architecture or shipbuilding process concern?
With the use of tungsten carbide tool materials, we done 14 millimeter shipbuilding materials. We did friction stir weld, but as you said, some limits have in friction stir welding. Especially we can done only butt weldings with friction stir welding. As thicker plates, yes, it's a problem, but the butt weld, only we can do butt welds with friction stir welding is I think more potential problems for the industrial using of this method.
Can we say maybe 10% of the whole welding may be done at the moment in the current technology using the stir welding? Shall we say that?
Yeah.
Approximately 10.
Approximately, yeah.
Okay. Another recommendation, while you are calculating the gas emissions, carbon dioxide emissions, you should take into account the emission spent or done during the production of these sticks or wires, because you take only the procedure of the welding, but not the ones you want to produce those materials. In stir welding, you don't have any supply material. The supply material production process also, emit some, gas.
Thank you very much. Thank you.
Any question? Otherwise, I'll move on to other presentation.
Thank you, Harold.
Thank you for your presentation. Okay, I'm inviting Mr. Fatih Alver to give his presentation. And the title, Advanced 3D Printing Techniques for Prototype Design in Wave Energy Systems. Here you are, please.
Thank you, Professor. Welcome to my presentation. I would like to introduce myself briefly. My name is Fatih Alver. I am working as a lecturer in the shipbuilding program at Ordu University. Today, I have prepared a presentation titled Advanced 3D Printing Techniques for Prototype Design in Wave Energy Systems. First of all, I would like to say potential of wave energy. In the renewable energy category, wave energy offers significant potential distributed across different sources around the world. These resources are waves, tidal motion, sea currents, marine thermal energy, and osmotic energy. The fact that 70% of the world is covered by water and about 44% of the population is located near the coast, increases the demand for wave energy day by day. The estimated theoretical wave energy potential globally is approximately 32,000 terawatt-hour per year. Other important aspects of wave energy are that it has a higher energy density than solar and wind energy. The energy obtained per unit square meter area is 2 to 3 kilowatt per square meter from wave, 0.1 to 0.2 kilowatt per square meter from solar, and 0.4 and 0.6 kilowatt per square meter from wind. Wave energy system prototype process. The prototype design of wave energy system is a complex process that presents several challenges. Irregular mechanical effects caused by sea motion significantly impact the structural and functional performance of the prototypes. Therefore, the unknown in the characteristic structure of waves demands serious testing of the reliability and efficiency of prototype designs. For example, the estimating process for prototypes requires long cycles during which unexpected problems can occur. Traditional production methods often remain inefficient in terms of time and cost to create complex structures, increasing the need for new technologies. Another challenge is the cost and time-consuming process of manufacturing physical prototypes. These challenges makes the need for 3D printing technologies that offer rapid production and prototypes that can be easily modified. 3D printers are a manufacturing technology that transforms digital models into physical objects layer by layer. The working principle of these devices starts with the creation of three-dimensional model in CAD software. This model is then converted into an STL file, a format suitable for printing. The slicing software that the printer will use then divides the model into layers for printing, and the production material is defined. The printer then starts to produce each layer with the specified material, and this process continues until a three-dimensional object is formed by adding layers on top of each layer. The main advantage of this technology is that parts with complex geometries can be produced. At the same time, this production method offers a more sustainable production process by minimizing material waste. Material used in 3D printers. 3D printers technology can respond to different needs of users with various material options. Figure 2 shows the types of materials commonly used in 3D printers and the structural advantages provided by these materials. The diversity of materials used provides many advantages, from aesthetic appearance to mechanical durability, from sealing properties to flexibility. This diversity expands the use of 3D printer technology in industrial and personal applications. A wave energy system production flowchart. If the wave energy system planned to be produced will operate near shore or offshore, it consists of three basic components. These are a floating platform, a mechanical system that converts wave energy into kinetic energy, and a power output until that converts kinetic energy into electric energy. All these components should be checked for functionality by designing prototypes at certain scales before real-scale production. Figure 4 shows the flow diagram of this process from the beginning to the production stage. In recent years, research and applications of 3D printing technology in wave energy systems have been increasing in different countries. Researchers have produced various wave energy converters using different 3D printing technologies and materials in their production. Chen et al. Developed a hybrid wave current energy converter that can harvest energy from both ocean waves and currents. In the prototype design, polyetheremite material was preferred for the production of the turbine using a 3D printer. As shown in Figure 5, this design reduced the starting torque of the turbine and improved the performance of the overall system by preventing water absorption. Wang et al. Designed a wave-driven turboelectric nanogenerator to harvest energy from ocean waves. The covers and basic components of the device were produced using PLA material with 3D printer technology. The 3D printed components have increased the efficiency and effectiveness of the energy harvesting system from wave motion, as they are accurate and weight reduced. Zhang et al. Developed a turboelectric hybrid nanogenerator to harvest energy from ocean waves. The mechanical structure of the turbine was designed in SolidWorks and produced with a 3D printer. As shown in Figure 7, the 3D printer design facilitated the lightweight construction of the turbine, increased the efficiency of wave energy harvesting, and improving the overall performance of the prototype. Rosenberg conducted a study on the design of wave energy converter and produced 1/130 scale physical model of the Triton WEG for experimental load test. As shown in Figure 8, the surface, structure, and reaction ring components were 3D printed. The surface was reinforced with glass fiber, and the ring was constructed from ABS plastic. The use of 3D printer has provided superior geometric accuracy and durability, which is critical for accurate load assessment in both experimental and numerical simulations, thus increasing the validity of the model for assessing design loads in different wave conditions. Conclusions. This study shows that 3D printers can be successfully used in the production of complex and marine environment resistance components such as wave energy conversion systems. In the literature, tests in terms of mechanical durability and corrosion resistance have shown that the material used are suitable for the marine environment and that the prototype do not lose performance in long-term use. Furthermore, systems produced with 3D printers have been observed to effectively improve the efficiency of wave energy conversions. However, there are still some challenges regarding the suitability for 3D printer technology for the large scale and mass production. Future work should focus on further increasing the material diversity and production speed of 3D printing technologies. In particular, the production of larger scale prototypes of wave energy system will be critical to assess the suitability of the technology for real-world applications. In this context, the role of 3D printing technology in the maritime and renewable energy sectors could expand further in the future and pave the way for innovative applications. Thank you for listening.
Thank you for your presentation, Mr. Alver. Any question to Mr. Alver for this presentation? Otherwise, I will skip it and will next presentation go on. No? Okay. Thank you. Thank you. Okay, I'm inviting the next presentation titled Usage Fields of Linear Programming Models and Evaluation in Terms of Ship Production Management. Mr. Here you are, please. Yusuf Genç.
Thank you, Professor. I am Yusuf Genç. I am working as a lecturer at the Galatasaray University. And we are working together with Mustafa Kafala and Uğur Burak Çelebi. And we are going to talking about usage fields of linear programming models and evaluation in terms of ship production management. Firstly, this is contents, introduction, and also linear programming, literature review, and finally, conclusion part. In mathematics, a modeling approach is used to generalize the solution of a problem or to obtain a formula that can reflect the solution with a general expression. Mathematical modeling is defined as the process of observing a phenomenon, making mathematical analysis, obtaining the results, and reinterpreting the model. Because the real world is too complex to describe, mathematical models simplify the systems and make some assumptions. Models cannot be exact reality, and however complex they may seem, they are an incomplete representation of real life. And here we have a figure, mathematical modeling process. We have two sides, real world and also mathematical world. In modeling, a real-life problem is considered as a mathematical problem. Some assumptions are taken into account in the development of the model, and the mathematical model obtained is solved, and the results are interpreted by comparing them with the real-life problem. Mathematical modeling is fundamentally an optimization method. Optimization, in general terms, is the process of determining the values to be taken by decision variables in order to optimize the value of an objective function formed with some constraints in a system. In optimization, modeling and analysis are two crucial steps. Modeling is the mathematical statement of a real-life problem, and analysis is the best solution that provides the model. And here we can see the general form of mathematical model. These models are generally called operations research, which can be defined as the process of finding the best solution to a problem in a system. In this way, scientific decision-making method is developed to understand the complexity of a system and to improve its performance. In addition, while decision-making processes are accelerated with optimization technology, decision quality is increased and real-life problems can be solved accurately. And the next part, linear programming. If an optimization model has linear constraints and a linear objective function, It's called a linear programming model and has most widely used area of operations research. It has a deterministic form. The objective and constraint functions in linear programming are first-order functions. These models are widely used optimization models. In general, modeling of industrial and economic problems is type of modeling based on the most effective use of limited resources in order to increase productivity in a production enterprise. It has assumed an effective role in modeling situations where profit maximization or cost minimization desired. And also here, we can see the closed form of linear programming models. Here, Z is objective function, and also it's a linear equation showing the desired goal in the decision-making process. And X is decision variables, and also decision variables are the values found by solving the mathematical model. B, right-hand side values. They are right-hand side values in the model and provide the information about utilization of scarce resources. And C, parameter in linear programming, uncontrollable variables such as matching capacity. And also E, technological coefficient, represent the value of the resource required for 1 unit of X. Here is one figure demonstration of the feasible region and optimal solution point. In the solution of mathematical models, the terms, we have some different kinds of terms. For example, feasible region, feasible solution, optimal solution, and optimal value. The set of points that satisfy the constraints in the solution of the problem represents the feasible region. And any solution in the solution space that satisfy the constraints of the problem is called a feasible solution. The optimal solution refers to the best solution determined among the feasible solutions. In addition, the value of the objective function as a result of the optimal solution is the optimal value. And we can see here literature review. Linear programming is used in many fields, such as transportation, mission, workforce assignment, marketing, nutrition, health, and also agricultural planning problems. For example, Zhu and Eng used linear programming models to perform energy efficiency analysis. They provided the results showing the efficiency performance of 21 OECD member countries with the proposed models. And also, Drzyjewicz and Bojic proposed a model for modeling and optimization of an industrial condensing system. They conclude that a saving of 60% in operating cost can be achieved. And the other one, Lahtelme and Hakonen, presented a linear programming model based on hourly load forecast for the cost-effective operation of a combined heat and power generation system. And the second part for this literature review, Sofia et al. Used a linear programming model for optimal land allocation in the production of 5 food products using data such as labor and emission wages. And also, Andrea and Andreen proposed a linear programming method to determine the optimal allocation of crops in agriculture. They tried to optimize profit by taking into account crop income and expenses per hectare. They observed that profit increased to 143% and cost decreased to 8% with the model. Akban and Ewok also used a linear programming model for bread produced in different sizes for profit maximization in bakery. The results obtained showed which type of bread is profitable to produce and sell. And also, this part, third, I can say, Romasian et al. Used a linear programming approach for planning of radiation therapy in cancer patients. The model was found to support orderly dosage adjustments. Another study in the field of health was done by Mulholland et al. On modeling of surgical service. In particular, they evaluated the effect of scarce resources such as operating theatres and intensive care units on financial results. They conclude that quality surgical care and optimal financial performance can be supported by mathematical models. And also we can say this part, linear programming can play an effective role in the efficient planning and utilization of resources in ship production management. Cost can be minimized by using linear programming methods, especially in processes such as workforce and machine assignments, scheduling of production stages, optimization of materials and components. In this way, the production process can be made more efficient. Furthermore, linear programming in the layout of workstations, stocks management, and production planning in shipyards can shorten ship delivery times by providing a faster and more organized production process. This is the conclusion part. We can say also this. It's seen that mathematical modeling is used at advanced level in our lives in many fields affecting our daily lives. The fact that a large part of the increasing world trade is carried out by ships causes an increase in the need for ships. Accordingly, it is inevitable for the shipyards to improve the production performance of the ships to be built. Thus, as in every field, the usage of mathematical models should be expanded in terms of managing the production processes of ships. Especially in workshops, this approach can play an effective role in determining workforce needs and machine usage times. Such models allow for the optimal allocation of resources at each stage of production process and base decision-making process on scientific grounds. Thus, production cost can be reduced and productivity can be increased. Thank you for the attention and listening.
Thank you. Any question? Miriam, please. Could you pass the microphone, please, to Professor?
Well, so in my university courses of ship design, I have a long chapter on optimization methods, linear and non-linear.
Yes.
Okay. You can even reduce some non-linear problems to quasi-linear problems. For instance, optimization, I checked it many years ago with Simplex, which I wrote myself following old texts by Indian mathematicians who were speaking about optimization since the 50s of the past century. And I realized that the mathematics written at least 60, 70 years ago. But what is difficult for engineers is to write the equation.
Yes,
put one of the first slides where you put epsilon equal to function of two variables. No? Our problems are function of vectors of variables,
yes,
which complicate things. So I'm not an expert in shipyards, but when I wrote, and first time I wrote my models for, let's say, CapEx, building cost in a shipyard, I learned for colleagues in Fincantieri that I have to split blocks in sub-blocks, sub-blocks, and each of these components has its own relation with different variables. So the problem is not quite easy to be applied. So I ask you if you can give us some example of what could be done, or maybe you have done it, you have not presented here. Thank you.
Okay. Thank you, Professor. We worked on especially block production processes in the shipyard with this kind of mathematical model, and especially also linear mathematical model and also stochastic mathematical model. With this type of mathematical model, we worked in the shipyard, and also, for example, we are producing block, and we have some stakes, for example, C, D, E, F, maybe you know this kind of parts, and especially we are working on worker times and worker performance. We are recording these situations, and also we want to know this, for example, what is the problem on the worker performance? For example, psychological situations, or there is a bad weather conditions, rainy or snowy, something like that. And this kind of situations, we want to apply this type organization, this type of mathematical model in shipyard, especially. Yes.
An explicit equation. It depends on many, for instance, is better to go to very detailed panelization or not? It depends. It depends on wage, and productivity is strongly related to wage. Professor Lambert many years ago demonstrated that there is a strict correlation between productivity and salaries to workers. No? And technology comes after. For instance, Fincantieri in Italy has a percentage of working cost on the whole shipbuilding, 17%. 17%. In South Korea, I refer to data I obtained 7, 8 years ago, I published in an economic magazine, was 23. It means that Fincantieri has a higher, they had more, let's say, robots and so on. But productivity is 70% lower than South Korea. It depends on management, and depends fundamentally on quality of ship design.
Yes.
Okay? And probably they are using mathematics more. for sure more than in Fincantieri, because in Fincantieri they are not using mathematics to plan anything. Okay?
Yes. Yes, yes. We have to compare the results with shipyard. Thank you.
Okay, thank you. Any more question? If no, I'm moving on the next presentation titled Length and Beam Extension Procedures in Black Sea Type Fishing Vessels. Okay, the other Dursun Saral, please go to point.
My name is Dursun Saral. I work at Karadeniz Technical University and work on Black Sea type fishing vessels. I'm telling about length and beam extension procedures in the Black Sea type fishing vessels. I am telling about reason for length and breadth extension of fishing vessel and Turkish fishing fleet and construct the instruction, the length and width of Black Sea type fishing vessel and length and breadth extension application. Decline in fish population, fishermen desire to catch more fish. Fish moving to deeper water due to rising water temperatures, and sonar causing fish to move, and fish migrating to open seas due to nose and light. Increase the volume of fishing nets, necessity for the ship to venture into open seas, prolong voyage duration and increased capacity requirements. Fishermen who cannot afford to commission new ship have extended the length and width of their exciting vessels. In this study, length and width extension application on Black Sea type fishing vessel have been examined and the practical implementation have been classified. Reason for length and breadth extension of fishing vessel. The increase in the volume of fishing nets, the need for more space on the aft deck. This has led to an increase in the width and length of ship from the stern and global warming, the migration of fish over the seas and deeper waters, the necessity of fishing in open seas. This has led to an increase in the depth of stem post, and this has led to the addition for a forecastle and bulbous bow, prolonged voyage duration, the need for larger tank capacities. All these reasons have made in necessity for fishing vessels to extend their length and width. A Turkish fishing fleet and constraint to increase the length and width of Black Sea type fishing vessel. In Turkey, the management of the fishing sector is the responsibility of the Ministry of Agriculture and Forestry. In Turkey, there are 1,610 registered fishing vessels, over 12 meters in depth, like purseiner, trollers, and auxiliary vessels. According to 2023 records, there are a total of 15,219 registered fishing boats engaged in marine fishing in Turkey. To ensure the sustainability of fisheries and reduce fishing pressure on stocks, the Ministry of Agriculture and Forestry has not issued the fishing vessel license for fishing in Turkish theoretical waters since March 29, 2002. However, after this date, a one-off time allowance of a 20% increase in length was granted to the existing fishing vessel to enable the construction over more modern and larger fishing vessels. Length and breadth extension application in Black Sea type vessel in three ways: length extension, length and breadth extension, addition of forecastle and bulbous bow with length and breadth extension. If ship lengths are available, the ship can be modeled in 3 dimensions, calculation can be made, and application can be carried out. If ship lengths are not available, measurements can be taken directly from the ship, modeled on computer, calculation can be made, and application can be carried out. If plans are not available, application can be carried out directly using measurement taken from the ship and calculation made. Length extension. If the length to be added is less than 4 meters, the length is increased after the rod extent reason to minimize damage to existing system and to realize application with minimum cost. If the length to be added is greater than 4 meters, the length is increased in front of the engine room bulkhead. Reason, to ensure longitudinal strength, to maintain the ability to change course, to maintain rotation control capability, to realize the application with minimum cost. Another way, length and breadth extension. With widening can also be done with widening. It can be done in 2 ways. The first method, as shown in figure 5, involves widening the vessel by extending outward from the side tank bulkhead only. It can be done if it is possible to have a displacement volume that can meet the increase in dead weight, minimal damage to system inside the ship. It can be realized at lost cost. The second method involved widening the vessel involved onboard port and starboard set from the bilge keel along the central keel, extending from the bow shoulder to stern. Reason, if the displacement volume is not sufficient to meet the increase in dead weight, it is done better preposition of the hull form. Addition forecasted and bulbous bow. Reason, to meet the maritime criteria for open seas, taking slamming capacity increase. The existing bow on the ship is cut from the shoulder and extended forward according to hull form. If design bulbous bow is added to the ship stem, if widening along with lengthening is required, the ship is cut along the bilge gate and expansion laterally. Some experiment. The vessel was cut into both shoulders with the entire forward section removed, and the remaining part was winded equally on both the starboard and port sides from the bilge keel. A length station with the permitted limits was applied, and a bulbous bow was added to the vessel. Another example, the vessel was cut at the bow shoulder, extended to the permitted length, and its breadth and depth were increased as much as available. A forecastle and bulbous bow were also added. To increase the vessel breadth, it was with and outward from the starboard and port tank exteriors. Length extension was applied from the stern, beginning at the rudder stock axis, and further length extension from the bow included the addition of a forecastle and bulbous bow. This section, bulbous bow and forecastle have been applied to ship, like this. And another example, the width and depth of the vessel have been increased. A forecastle and bulbous bow have been applied to ship. Another example, the depth of the vessel has been increased. A forecastle and bulbous bow have been applied to ship. Concluding with the development of fishing industry, fishing vessels have also involved. Due to the number of fishing vessels and the decline in fish population, the issuance of new vessel lines have been determined. However, 20% length extension equivalents have been created for the modernization of existing vessels. Over time, the techniques for length extension specific for vessels have extended based on shipowners' requirements and have become applicable today. Thank you for listening.
Thank you for your presentation, Dursun. Any question?
I want to add some comments and one question. Unfortunately, there's a very good correlation with the killing power of a fishing boat and its length times beam times draft. So this is a bad news for the fish and also for the future of fishing. However, arbitrary length is also bad for the fishermen. So we have to protect the fishermen, we have to protect the fish. So what I can possibly suggest is that when you decide on what to do to an old boat, fishing boat, it's best to think about the fishermen, and that means the acceleration levels where fishermen are working. And it's also good to think about the fuel, and you are doing that by adding a bulbous bow, for example. But also the stern can be changed a little bit, and then the beam can be modernized by nice form, not straight, but a nice form. So that's my comment. The question, when you propose something, do you also check what it will mean to the operation of the hull, for example? Or is it an arbitrary decision to increase the length by, say, 5 meters or 2 meters or something like that?
Yes. Some ship owners have the money and the Ministry of the Development don't permission for the new fishing vessel, and some owners have no money, and owners selection the extension with the ship. Yes.
One more question, I think.
I'd like to know which is the payback period for such investments. So fisheries are reducing. Where? In the Black Sea? In the Aegean Sea? Because for instance, in Italy, in the western side of Sardinia, the so-called Mar di Spagna, it means the Mediterranean Sea between Sardinia and Spain is very rich. Ships are going in deep waters, okay? Japanese fishing vessels, huge ones, 60, 70, some even 80 meters long, are coming. They fish international waters without any problem, with laws, with anything, and are selling their good fish in Milano at prices. Sushi in Milano is the most expensive sushi in the world. In Tokyo, because the fish is very good. So I wonder why in Turkey, your ministry, no, don't plan like they are doing in Norway now, to build new fleets, industrial fishermen. These are, they say, in Italian way to solve problems. They are not solution. Then a technical comment is quite, since many years, many decades, I can say, demonstrated that bulbous bow has advantages if you have to run to the market. Let's say 14 knots fishing vessel, 30 meters has full number 0.4, 0.42, and then the bulbous bow is convenient. But if they have not to run so fast, 14 knots, it has counterindication for seakeeping, for safety of fishermen on board. The bulbous is against seakeeping. And so, which is a right compromise. It depends on many conditions. I don't know the condition, but I have some knowledge about this because many years ago, when Turkey was still candidate to enter into the European Union, I worked for bureaucrats in Brussels for a research fishing vessel, okay? And I received from oceanographic expert in Turkey a lot of information. I was acquainted, because I ignored it before, that fish, different types of fish have a different hearing frequency, and the problem of noise, hence the propeller rate of revolution has to be made different according to different zones in the Black Sea. Okay? Yes. So the problem is quite interesting and complicated. It would be interesting to cooperate with a person who is a big expert. He built his own UBC service. Quite no? You have some expert here.
Yes, thank you.
Okay. Thank you. Okay, the next presentation is titled Comparison of Life Cycle Assessment and Maneuvering Techniques for Glass Reinforced Plastics and HDPE Boats. I'm inviting the presenter, please, to the podium. Mr. Ayberk.
Thank you, Professor. I am Ayberk Sözen from 9 Eylül University. Today, I am going to present you comparison of life cycle assessment, LCA, and the manufacturing techniques for glass, reinforced plastic, and HDPE boats. Okay, today I am going to talk about a little bit for the HDPE boat production and the GRP boat production. After that, I am going to talk about our methodology for LCA, and I'm going to give our results, and I'm going to conclude. At the end, I am going to talk about a little bit for our future studies about this topic. Okay, we are using HTP in marine industry for different sectors and for the different purposes. One of them is the fishing nets. We are using it for the pipes, underwater pipes, for the internet, for the other things. We are using HTP in fish farms. We are using HTP for the small patrol boats up to 20 meters. 20 meters is a logical limit. Over 20 meters, it is possible to build an HTP boat, but it's not very feasible because HTP is a flexible material. There are some problematics for the structural integrity. That's why 20 meters is a limit. We are using it for the sailing boats, fenders, pontoons, and kayaks. HTP is a very popular material for the plastic industry. But unfortunately, for the marine industry, we started to use HTP approximately 20 years ago. And for the HTP, for example, patrol boats, we see the HTP patrol boats, especially in last 5 years, mostly 10 years. HTP includes 30% of the all thermoplastic production. The advantage of HTP for the boat building, it's easy to recycle because it's a thermoplastic. There is no cross-links like thermosets, like epoxy or polyester or vinyl ester. You can remelt and you can reshape very easily, up to 5 times. There is a high impact resistance. You can punch with a hammer to HTP boat and it's nothing going to happen. It gives a very big advantages in case of grounding or accident damage. There will be only small stretches, nothing more. There is no corrosion. You don't need an anti-fouling paint because it's a low surface energy material. Nothing can stick to HTP. That's why you don't need an anti-fouling paint. That's why the maintenance costs are lower. And there is a long lifespan. Exactly, we don't know the lifespan very well because it's a quite new material for the shipbuilding industry. But approximate lifespan is more than 40 years. Okay, actually, we are building HTP boats over 5 meters, generally like steel shipbuilding techniques. We have HTP plates, we bend them, we weld them with a plastic welding, but it's quite easy and it's very safe, especially for the occupational health and safety measures, because only small odor, there is nothing more, there is only few CO2 emissions. Another technique that we generally use for the HTP boats less than 5 meters is a rotational molding. The mold is turning very quickly due to the gravitational forces. The plastic pellets goes to the exterior shell of the mold and it became solid with heat, and we can remove the boat and we can open the mold. We generally use this technique up to 5 meter HTP boats. And for the GRP boats, in this study we used hand layup method for the comparison for the LCA. Hand layup method, it's generally less costly, it's more easy, but it's heavier because the resin and the fiber ratio is not quite good. The vacuum infusion is becoming very popular to build a light boat because you can vacuum the excess resin. And the GRP boats are most cost effective if you are building mass production. it's costly to build the mold, but after that you can build the boat very easily. It's lighter. You can work with amorph forms. That's why it's more appealing, especially for the yachts. HTP boats are generally using for the work boats, but for the GRP you can use them to build yachts. It's fast to produce, it's more rigid, and we have more know-how because we are building GRP boats more than 30 or 40 years. In this presentation, in this study, we made a LCA life cycle assessment to compare HTP boat production and the GRP boat production by using a special life cycle assessment software. But I would like to say that we just compared the production method. We didn't compare the whole process. We didn't include the operational process and the recycling process at the end of the life cycle. We took the real data of the 5 HTP boats and we took the data of the electricity need to produce them. And we assumed that if we build these boats from GRP, how many hours, how many times that we are going to need, and we assumed we tried to calculate the electricity need as well, just to compare the both materials. We took 5 boats from 16 meters to 5 meters. Okay, for the results, especially the GRP needs more electricity and it causes more CO2 emissions. HTP is more sustainable. It requires less energy to build, especially if you go to bigger boats, longer boats, this difference increases. To conclusion, although HTP appears to be a more environmentally friendly material, solely in terms of production, its advantages extend far beyond this. The ability to recycle HTP at the end of its life cycle and its minimal maintenance requirements make it a significantly greener alternative to GRP. HTP also offers significant advantages in terms of worker safety, unlike GRP, which involves the handling of potential hazardous materials such as fiberglass and resin that can cause skin irritation, respiratory issues, and long-term health risks. HTP production is generally cleaner and involves fewer harmful substances. This reduces the exposure of workers to toxic chemicals and airborne particles, creating a safer and healthier working environment in manufacturing facilities. For the future studies, we aim to investigate the vacuum infusion method as well, and we would like to include all the process, the operational process and the recycling process at the end of the life cycle. Thank you for listening, Professor.
Thank you very much for your presentation, Ayberk. Is there any question? We can get them. One question, please.
Okay, thank you for your presentation. My question is about this life cycle assessment of those types of boats. When they run into any other boats or any object, is it possible to repair quickly, or how quickly can be repaired compared with the GRP types of material used boats?
If I understood very well, we want to compare the repairing possibilities of HTP with GRP. Actually, repairing HTP, it's quite easy. You just need a welding machine. You can cut them very easily. It's like steel shipbuilding, but it's more your tolerance. It's more higher. That's why you don't need a very skilled, very experienced worker to maintain or to reshape or to build.
Thank you.
Any question? One more question.
Thank you for the presentation. My question is that I think the functional unit of the study was, what was that? My functional unit of the study, what was that? You calculated everything for separate ships? My first question is that, and also the second one, the life cycle impact assessment methodology, which one was applied? I think it was only the software and the background database. I'm curious about.
Honestly, actually, I have expertise on HTP boat production, but one of our professor, Mehmet, is not here. He is the expert for the life cycle assessment, but you can email him. For the boat, we try to calculate all the process, and there is an equivalency for the electricity that they said to me.
Okay, thank you.
You're welcome.
Thank you. Thank you.
Okay. Okay, let's go on. The last presentation, titled Friction and Wear Performance of Crane and Thick Rail Coatings Deposited on Cam Tappet Ships. Mr. Semih Mahmut Aktarer.
I'm sorry. Thank you, Professor. Ladies and gentlemen, my name is Semih Mahmut Aktarer. I am working in Recep Tayyip Erdoğan University Vocational High School. I am going to talk about friction and wear performance of chromium aluminum nitride and titanium chromium aluminum nitride coatings deposited on cam tappet shims. My content is following introduction and experimental procedure, result and discussion, including structural properties, such crystalline size and lattice strain, and friction and wear behavior, and then conclusion. Internal combustion engines continue to be main source of power for transportation. The engines are responsible for 10% of carbon emissions. The valve system accounts for about 10% of total engine friction losses. And important friction, these losses occurring at the cam taper contact in the valve train. Tribological improvements in the valve train extend component life, reduce maintenance cost, and contribute to efficiency of the engine, decrease both fuel consumption and greenhouse gas emissions. Chromium aluminum nitride and titanium aluminum chromium nitride coatings were deposited onto the shim using a reactive magnetron sputtering technique. PVD, physical vapor deposition. X-ray diffractometer was employed to examine the crystalline characteristic of the coatings, and the chemical composition and microstructural properties of the coatings were analyzed by scanning electron microscope, SEM, and energy dispersive spectrometry, EDS. Micromechanical properties of test coatings were determined using a non-indentation test. Experimental procedure carry out reciprocating turbometer. The reciprocating wear test was carried out to determine the friction and wear behavior of coated shims. Tungsten carbide ball with a diameter of 6 mm was used as a counterpart, and the test was carried out under the lubricated condition. As you can see, ball speed 10,000 cycles and sliding stroke of 5 mm under the load of 30 newtons. Result and discussion is structural properties. You can see cross-sectional SEM image and surface EDS analysis for chromium aluminum nitride and titanium chromium aluminum nitride coatings. The thickness of the chromium aluminum nitride is 2 per 2.9 micrometer, and titanium chromium aluminum nitride coating is about 3 micrometer. The average surface roughness chromium aluminum nitride and titanium chromium aluminum nitride coatings was 0.11 micrometer and 0.17 micrometer, respectively. The EDS analysis revealed that the composition of the chromium aluminum coating, as you can see here, and the chemical composition of the titanium chromium aluminum nitride coatings surface was found to be as here in slide. The XRD result showed that the three main diffraction peaks correspond to crystallographic planes 1, 1, 1, and 2, 0, 0, and 2, 2, 0, respectively. The chromium aluminum nitride coating exhibited a preferential orientation on 2, 0, 0 crystallographic planes, and chrome nitride and chrome 2 nitride. In the titanium chromium aluminum nitride coatings, the preferential orientation was observed on 1, 1, 1 crystallographic planes. It's well known that the diffraction peaks shift to higher angle with increasing aluminum content. This is confirmed by the fact that the diffraction peaks in the chrome aluminum coatings are located to the right of the standard chrome nitride diffraction peaks. The diffraction peaks of both coatings are located between the titanium nitride and aluminum nitride diffraction peak. You can see table 1 structural properties such as nano-hardness and elasticity modules, and structural properties, crystalline size and lattice strain. Titanium chromium aluminum coating exhibit higher nano-hardness and elasticity modules than chromium aluminum nitride coatings. One of the primary reasons for this is that the titanium chromium aluminum nitride coating exhibit a smaller crystalline size and higher lattice strain. The higher ratio hardness and elasticity modules of the titanium aluminum nitride coatings in the comparison to chromium aluminum nitrides indicates that it offers a structure that is more resistant to plastic deformation. The smaller crystalline size and higher lattice strain positively affect both hardness and resistance to plastic deformation of the material. You can see illustrate friction coefficient curves of the chrome aluminum nitride and titanium chromium aluminum nitride coatings. The average friction coefficient of substrate, chrome aluminum nitride and titanium chrome aluminum nitride coatings are, you can see as here. The lower average surface roughness of chrome aluminum nitride coating facilitates the uniform distribution of the lubrication film on the surface, thereby reducing the friction coefficient through the minimization of the tribological contact. The lower lattice strain chrome aluminum nitride and the potential formation of chrome oxide tribofilm can be additionally reduce friction and provide a stable performance. The SEM image of the wear track of the substrate of both coatings. The worn surface of the substrate display clear grooves marks. An abrasive and adhesive wear mechanism was observed to be occurring on the substrate. The worn surface of the chrome aluminum nitride coating display a multitude of the delamination and micro cracks. You can see figure B. However, the delamination and micro crack formation is significantly decreased on worn surface of the titanium chromium aluminum nitride, and you can see figure C. The titanium chromium aluminum nitride coatings exhibit superior resistance to wear compared to chrome aluminum nitride coating due to its higher non-hardness and elasticity modulus. The worn surface of the chrome aluminum nitride coating exhibited numerous microcracks. These micro voids inherent to the reciprocating test process contributed to the formation of microcracks on the coating surface. As a result of microcrack propagation, the surface displayed distinct brittle fracture features. EDS analyses revealed the presence of iron on the worn surface, indicated localized peeling of the chromium aluminum nitride coating. However, the high concentration of coating elements suggests that the coating's protective function remained intact. In contrast, EDS analyses of the titanium chromium aluminum nitride coatings worn surface detected a significantly lower iron content and a higher concentration of coating elements. This observation confirmed that the titanium chromium aluminum nitride coatings largely remained adherent to substrate, preventing complete peeling. And the wear track profile and wear rates of the substrate, the chrome aluminum nitride and titanium chrome aluminum nitride coatings. The wear track profile in figure reveals that the substrate exhibits deepest wear track, indicating severe wear damage, while both coatings show significantly shallower tracks, reflecting enhanced wear resistance. Among these coatings, titanium chromium aluminum nitride displays the lowest wear depth, corresponding to its superior mechanical properties such as higher nano-hardness and resistance to plastic deformation. The substrate shows the higher wear rate, followed by chrome aluminum nitride with the titanium chromium aluminum nitride coating exhibiting the lowest wear rate. And conclusion, These results suggest that the titanium chromaluminium nitride coating is an effective option for shim pair application due to its low wear rate, while chrome aluminum nitride coating is advantageous for its low friction behavior. Overall, the titanium chromium aluminum nitride coating emerges as a promising alternative, particularly for application demanding high durability. Thank you for your attention and listening.
Thank you. Is there any question? If no, we are done all presentations, and I'm ending the session. Thank you for listening and your patience. Hope to see you again.
Dear participants, there will be a coffee break, and after the coffee break, the closing ceremony will be held in Salon B.